Good morning, Astronomy 1020, and welcome to the second part of Lecture 3, where we're studying Newtonian mechanics, gravity, forces, and things that go bump in the night. Today will be a very important lecture where we master Newton's law of gravity, and we're going to be performing some complex calculations in our homework session today, where we will do the Chapter 4 homework. So hang on to your hats. We're going for a little ride. I'm just going to check and make sure. Okay, everything's up to snuff here. So let's say that you looked up Sir Isaac Newton's hometown on Google. Newton was an English scientist. And if you go to Google and you type in Woolsthorpe, as in Woolsthorpe, England, this town is famous for being the birthplace of Sir Isaac Newton. I spelt it wrong, but okay. And sure enough, if you go to the image search, the first thing that comes up are pictures of Isaac Newton's ancestral home, which still stands there today. And there's kind of like a cool story about this. Oh, here's, there's an apple tree that's still in the front yard there. Newton had to leave college, I think Trinity College, for a similar reason to the reason why we're doing our classes on Zoom today. There is a national pandemic in the form of the bubonic plague, and people did not understand exactly what was transmitting it, but they were concerned that it was the dirty city air. It, of course, turned out to be rats and mosquitoes transmitting the disease to people through mosquito bites, but they thought it might be the dirty city air. So because the pandemic was infecting so many people, Newton, just like you guys, had to leave college and go home and sit in his bedroom and study his textbooks in isolation. And the books that he brought with him were books by Johannes Kepler and Copernicus and Tycho Brahe and Aristotle, all of the great classics of the ancient and, for him, more modern world. And while sitting there reading these books, he came up with some profound thoughts and realizations that were probably inspired by Kepler's laws of planetary motion. For instance, you guys know that the second law of planetary motion that Kepler gave to us was the law that goes equal areas and equal times. And the equal areas and equal times law tells us that as the planet travels on an ellipse, it sort of speeds up and gets faster as it goes closer to the sun, and then it travels slower when it's farther from the sun. And Kepler actually wrote about this because he was kind of like this astrology crackpot mystic. And he believed there was some kind of a magical vitality thing that stretched between the sun and the planets. And he said, it's so interesting how the planet speeds up as it gets closer to the sun. It's like it has this living vitality, this, I don't know, this something. And he couldn't put his finger on the last word, which of course was force. It was Newton who made the leap to say, this is a force. And as the story goes, Newton claims in his journal that he was occasioned by the fall of an apple. So he saw an apple fall from a tree, and he said, this made a deep, profound effect on me. I realized that the same forces that are going to pull that apple down to the ground, those are the same forces that are going to hold the moon in its orbit. And he connected things dropping in Earth's gravitational field to the gravity of Earth extending out into space and holding the moon in its circular orbit. That was a sort of profound realization. Now, I can't tell you exactly how he derived his law because it's a little bit complicated. I guess you could read about it yourself in the Principia Mathematica if you've got a few hours to spare. But what I will do is I will show you the form that Newton originally came up with. He connected gravity to two important concepts. One, he connected gravity to mass, that objects, whether they be planets or ping pong balls, they have mass associated with them, and that mass was the origin of the attractive force of gravity. For some reason, nature wants masses to stick together. And he also realized that distances were involved, that as the particles got farther apart, the gravitational force should get weaker exponentially. And eventually, he sort of came up with this form, which we will start with today, for his law of gravitation. Let me share screen, go to my slideshow, and scroll down to our law of gravitation. This is a lovely little slide here showing you the kind of setup that we want to consider. We have two massive objects, which in this diagram have been labeled M1 and M2. For our practice calculation today, we'll probably try to calculate the gravity between Earth and the moon. So we could imagine that M1 is the Earth and M2 is the moon, but they really could be any two masses at all, even two bowling balls floating in space. And they're separated by some distance d. And I'd like to point out that the distance d is a center-to-center distance. That's going to turn out to be an important point in many of our applications. The distance is from center to center of the two objects. Now, the eventual law of gravitation that we know today looks something like this. There's a constant of nature called big G, which I'll talk about in a moment. The force of gravity is proportional to the product of the two masses. So you multiply the two masses, and then you divide by the distance between them squared, where we're going to want to pay very close attention to the square because that turns out to be quite meaningful. The way that Newton originally wrote his law of gravitation would look like this. Let's take some notes. Newton's law of gravitation. And this first version that I'm giving you, we're going to call it Newton's style, because this is why we've named it after him. He wrote that the force of gravity is proportional to the product of the two masses and inversely proportional to the square of their distance. Where for some of you cats, I have introduced a new mathematical operator that you may not be familiar with. The little Jesus fish there is a new mathematical operator that's a little bit different than equals. It means proportional to. And believe it or not, it is a powerful math tool that can let you evaluate equations easily and quickly, sometimes without even using a calculator. Why do we use the proportionality symbol? The proportionality symbol kind of means that the force depends upon these variables, but it is not exactly equal to these variables because you have to throw in some other numbers or constants with units. What's important about the proportionality symbol is when you write this, you know that these are the important parts of the equation that can change. In each new scenario, the masses can be different and the distances can be different. So those are variables that change. When we use the proportionality symbol, we can use it not to evaluate the magnitude of a force. Do you guys remember what the units of force are? Let's do a little memory jog here. What units do we use to measure force in the MKS system?
Length.
Nope.
Kilograms.
Kilograms are a unit of mass. Meters are a unit of length. We're looking.
Seconds.
Seconds are a unit of time.
Newtons.
Newtons are an MKS unit of force. That's right. Where 1 Newton is equal to 1 kilogram meter per second squared. Okay, good. That was a useful exercise. Later on, when I show you the real force of gravity, I'm going to put an equal sign there, and when we plug in our numbers, we'll get a force in newtons, like 25 newtons. But the purpose of the proportionality symbol is to ask us questions like, suppose I'm not really interested in knowing just how many newtons the force is. What if I'm interested in knowing the answer to a different type of question? What would happen if I doubled the mass of Earth? How would the force of gravity between Earth and the moon change? What if the moon was moved 2 times farther away? How would that affect gravity? This is what the proportionality symbol is used for. And the way it works is you basically get rid of all the variables except the ones that you're varying, and you just kind of plug in the numbers by the number of factors by which you're varying it. That probably doesn't sound like much. Let's just show an example. Here's an example of how to use proportionality symbol. You would say something like, suppose I double the distance between two masses, M1 and M2. In this case, the masses do not change, and I would rewrite the proportionality symbol as the force is inversely proportional to the square of the distance. Notice that I keep distance in the bottom and I keep the square with it. I've not written down the masses because they're not changing, they're staying the same. Since I'm doubling the distance, I'm changing it by a factor of 2, and then all I have to do is plug in 2, the factor by which I vary the distance. Now, since I have a little math problem, you're going to see me change from proportionality to an equal sign. And you guys probably know what 1/2 squared is, right? Please tell me you know what 1/2 squared is so I don't have to go and shoot myself in the kitchen.
1/4.
Okay, right. So 1/4. And the meaning of this, the meaning of what you have just done there would be like this. If you double the distance, the new force is 1/4 the original force. The new force is 1/4 the original force. Another way to say that, an equivalent way, would be 4 times weaker. The gravity would get 4 times weaker. So you see, I didn't use proportionality to calculate the force in newtons. I used proportionalities to find out how many times the force will vary. If you're just learning this, this probably seems really stupid and not that all interesting, but I swear to God, physicists can quickly evaluate mathematical equations, even very complicated ones, by playing games like this. Okay, let's see if you guys can do what I just did. So I'll give you a little test here. First of all, make sure you write that down. Can I erase this? Okay, I'm doing it. Okay, someone who's like hanging with me here today, I'm going to give you a sample problem, and I want to see if you can do what I did and use the proportionality constant. Suppose I double both masses. So that's the setup. I'm going to double both masses. How does the force of gravity vary? First thing I want you guys to do is set up the proportionality symbol. Force is proportional to what? What are we varying in this sample problem?
Mass.
Mass.
Both masses. So what should I write after the proportionality symbol?
M1 squared.
No, we are not squaring M1. The squares are sacred. If there were squares there, we'd have to keep them, but there are not squares there. So try again. Sorry, who said M1 squared?
M1, that's me. M1 times
no.
M2.
That's right, Philemon. M1 times M2, because we want to leave them just like they are. Notice Philemon did a good thing. Now that he's corrected himself, Philemon did not include the distance because we are not varying the distance here. It's not changing, so you don't need to include it. You just focus on the variables that are changing. If I had doubled one of the masses, we would just have M1. But because I'm doubling both masses, we have to keep them there. Okay, what do I do next, Philemon? You seem to be following me here.
Parentheses squared.
I'm sorry, can you, what I want to do is I want to write another proportionality, and now I want to substitute in the factors by which they're varying. Does that make sense? I don't know. Basically, I'm asking, what do I write next? Do you know?
Times 2.
Huh?
Times 2.
Like this? When you say times 2, that's what I'm.
Yeah, or M1 times M, well.
We already got the M1 times M2. Now we got to substitute in the factors by which they are varying. So let's take it slow. By what factor is M1 varying?
2.
So you write in 2 times by what factor is M2 varying?
2 to the power.
So I don't know if it was an audio thing, but what I heard from you, Philemon, was times 2. That didn't make sense to me. 2 times 2 makes sense to me. Do you see?
Yeah, or you couldn't do parentheses 2? Or is that just bad math?
When you say parentheses 2, that's what I'm thinking.
Yeah, and that's what I'm thinking.
But that's not right. We have to sub in for M. That's a single factor, but we have to sub. Sorry, is it? Yeah, it's factor. That's a single factor, but we have a factor for M1 and we have a factor for M2. Where I think I'm using the term factor appropriate. Factor is when you multiply things, right?
Yeah.
This is a factor, that's a factor, that's a factor.
Yeah.
But a single 2 is only one factor, but we have 2 factors. Do you see?
Mm-hmm.
So it's.
Yeah, I'm just wondering if you put parentheses around it. So I'm just trying to see, after you do the proportional, does that mean times? That's why I'm getting.
No, proportionality does not mean times. Here's what I want you to think about proportional. It means I am a weak ass equals sign that is not as strong as equals. I really don't know how else to put that, okay? I'm a weak ass equals operator, okay? Except I'm not really that weak, I'm strong. It's like a subtle thing. It's like, like the first time you have blue cheese, you're like, that's kind of fucked up, there's mold in it. I don't know how I feel about that. And then you start to think, oh man, that actually tastes really good. I like how funky that is. So that's what's up with this. This is the blue cheese of mathematical operators. It's going to take some time for you to get to understand why it's cool, all right? All right, so we substitute in doubling the mass 1, the first factor. We then substitute in doubling mass 2, the second factor. And now we turn it into an equal sign because it's not vague anymore. We're actually doing some math. And the answer is, obviously,
4.
And what does the 4 mean, Andrew?
For like the gravitation.
The force of gravity, the new force. Anyone?
4 times stronger?
That's right.
Yeah.
So notice, if you simultaneously doubled the mass of Earth and doubled the mass of the moon, the gravity would get 4 times as great because each mass contributes as a factor. Now, I want you to hear me read this equality the way that Newton wrote it. When Newton wrote this down in his Principia Mathematica, I did go and I fished this out once because I felt like as a physics student, I owed it to Newton to go back and read his original words about it. And I was blown away to discover he didn't write it down in this math format. He wrote it out like in literary English words. And his words went like this. It can be deduced that the force of gravity is directly proportional to the product of the two masses and inversely proportional to the square of their distance. That's how they did math back in that day. So if you think this is bad, man, you don't want to go messing around with this stuff, okay? But the words mean something. Directly proportional means I'm on top and I multiply. Inversely means on the bottom, and square means there's a little 2 there, okay? All right, we'll try more examples with that in our first homework today. Now I'm going to talk to you about how we go from this weak ass equality called the proportional symbol and turn it into an equal sign. In some ways, it's about units, and also in some ways, it's about experimentation and making sure that we ask nature about her feelings about gravity. Let's consider it from the point of Mks units, which you guys know about. If I'm a human being and I'm investigating nature, what are the units that I should most properly use for mass? What Mks units do we use to measure mass?
Grams?
Kilograms, right? Is that what you said?
Yes.
All right, like these guys. Okay. And remember, the kilogram is a human invention. Mass might be understood by nature, but it was humans who imposed upon her our idea of what a unit of mass should be. We decided that masses should be measured in half a brick quantities, okay? What MKS units do we use for distance?
Meters.
Kilometer.
That's right. And once again, meters are a human being construction. Nature may understand space and distance, but we imposed upon nature our idea of what a good measurement of distance should be. And for some reason, we decided that we would measure the entire universe in these meter sticks, okay? And how about our MKS units of force? We've already talked about this. They are
Newtons.
right. And remind yourself that a Newton is a kilogram times meter per second squared. In other words, because we invented the kilogram, the meter, and the second, we also invented the Newton. And therefore, once again, we have imposed upon our vision of nature what a proper unit of push or pull should be. But now it kind of gets down to the business of the universe itself. Remember that if we take two massive objects, I don't have 2 kilograms, so I'm going to take this granite stone, and I'm going to take this iron meteorite. They clearly both have mass. According to Newton, there should be a gravitational attraction between these two things. In fact, I bet if I put them out into the vacuum of space, millions of miles from any star or galaxy, kabillions of miles from any star or galaxy, and I just delicately place them into outer space, they would slowly begin to attract each other just because of the magical attraction that mass has for itself. The problem is nature decides how strongly to pull based on mass. And we need to ask nature's opinion. If I take 1 kilogram and another 1 kilogram mass, and I separate them by 1 meter, just how strongly do you plan on pulling? Newton realized this because he was a clever fellow. He realized that he had to ask nature to find out what the proportionality constant was to turn this into an equal sign. If you want to know what the strength of the force is, you have to know how strong nature is going to pull. But here's the problem. Because gravity is such a weak-ass force, he didn't have a way to measure it. I don't suppose anyone out there knows who did measure it. Kind of a famous historical thing.
Einstein?
Not Einstein. Einstein did do stuff. We're going to learn about Einstein in this class, and we're going to learn about his contributions to gravity, which were immense. But these guys had to do their work first before Einstein could come. So the guy comes before Einstein, but after Newton. His name is Henry Cavendish. And you won't learn about him in your book, so I want to tell you about this, because I think his experiment was just so Cavendish, so wild and cool that he pulled this off. So Henry Cavendish, sometime between 1730 and 1800, performed this legendary experiment where he measured the strength of gravity. He had already known about Newton's proportionality argument. Basically, Cavendish had read Newton's paper, of course. And he performed this experiment. I was going to see if they had a picture. Let's just type in Cavendish experiment, where he came up with a method of measuring the strength of gravity. Now, check out how ingenious this is. I really love experimental science. I think it's so wild. We've since continued to reproduce it today. Here's, I think, an illustration of his original work, but if I show you a simpler diagram, you'll get the picture a little better. Let's see, which of these diagrams is the least confusing? Probably this one. He actually got gigantic lead bowling balls, and I think he chose lead because the density was so great, he realized he'd have a greater chance of actually measuring a deflection. And he put these large masses, these spherical lead spheres, on what's called a torsional balance beam, or I guess it was probably on like a stationary beam. And then he took these smaller lead weights, which are maybe the size of, tennis balls, and he suspended them from what's called a torsional balance beam. And that's a rod that is suspended by a very delicate fiber that can twist back and forth. And because they were kind of dangling and balanced by gravity, gravity could actually pull the little spheres towards the big spheres by a microscopic deflection, one that he could measure. In the modern version, we shine a laser beam onto a mirror. And even if the deflection is wicked, wicked tiny, as long as you bounce the beam off the mirror and send it really far away, you can measure the angular deflection and measure how strong the spheres are being pulled on. Now, try to understand, what blows my mind about this experiment is he took spheres that were essentially, you know, what do I have here? Like the size of this globe, or maybe a little bigger. And he was actually able to measure gravity tugging on spheres of just these small sizes. I never would have thought it was possible, right? And he figured out how strong nature likes to tug on gravity. But what's so cool is he didn't really appreciate at the time what he was doing, that he was measuring the index of the strength of gravity. What his goal was in doing the experiment is, in his time, no one had a method of measuring what the mass of Earth was. So ironically, he wasn't interested in the forces of nature aspect of it. He just wanted to find a way to estimate how much mass was in the Earth. And when he published the paper, he published it as on a new method of estimating the mass of planet Earth. And it, of course, was a big thing. It was a big science splash. But only afterwards, years afterwards, people went, holy shit, bro, you figured out how to measure the strength of gravity itself. And that's kind of way more profound. So once Cavendish did this work, so this is going to be now, we still call it, of course, Newton's Law of Gravitation, but I'd like to point out that it would not have its current form. I call it Cavendish style, right? And now we can turn our weak-ass proportionality into a strong-ass equals, and we now have this equation. The force of gravity between two objects is a magical number measured by Cavendish called big G times m1 times m2 divided by the distance squared. Allow me to introduce what is known as the universal gravitational constant, otherwise known as capital G, and it has a value of approximately 7 times 10 to the minus 11, and the units are kind of wacky, okay? The units are meters cubed per kilogram per second squared. And what this thing is, if you have to understand it in some way, is this number is an index of the strength of gravity itself. So Nick Souza, what do you think? What does it mean if the gravitational constant, which is universal to every mass throughout the universe, is 7 times 10 to the minus 11? Like, what would that number look like if you were to write it out as a decimal?
Oh boy.
0 point, what would I have to do? I want everyone to understand what this little tiny number means.
So it's a negative 11th. That would be 11 spaces to the right of the decimal. Right?
How many zeros would I have after the 0 point?
11.
No, that's not how this works. Negative 11 means the 7 is in the 11th place. That means there are 10 zeros. 1, 2,
Oh, okay.
4, 5, 6, 7, 8, 9, 10. And the 11th digit is a 7.
Okay.
Okay. I'm glad we did this. Meters cubed per kilogram per second squared. So what does that tell you, Nick, about gravity, if that's the index of the strength of gravity?
It's very small.
Not only is the number small, but take one more leap with me here. That means gravity is
Weak.
Anyone follow me?
Weak.
Gravity is a weak-ass force. It is the weakest of weak-ass forces, okay? In fact, gravity is so stupid weak that you only really start to notice gravity exists at all once you have an epic planet-sized lump of rock and metal. You literally need a sphere 12,000 kilometers thick of rock and metal before you even start to notice, hey, I'm stuck to this thing for some reason, right? I mean, face it, if I take two ping pong balls and I hold them up, there should be a force of attraction between them, but I don't feel it. That's because if we were to calculate the force of gravity on these two objects, it would be, well, actually, you know what this means? If we had two 1 kilogram masses, so I only have one because I broke the other one in a daring do experiment, but imagine I had two 1 kilograms, and imagine I separated them by 1 meter, about yay far away, about the length of this board. 2 kilogram masses separated by 1 meter would have a strength of that many newtons, right? Because if you plug in 1, 1, and 1, you'd get 7 times 10 to the minus 11 newtons. So that's a pretty pitiful force, especially considering that the force that gravity is tugging on this right now is 10 newtons. So gravity is just, it's such a subtle force. The only reason we know it exists is because planets are massive and stars are massive, right? In fact, a lot of the problems that people have when they send these space missions to small asteroids and small comets is, even though the comet might be like 12 kilometers long, like the size of the greater city of Providence or something, even then, when you have a city-sized lump of rock, gravity is so weak that the spacecraft, when it tries to land, can accidentally bounce off the surface and just fly away into space. So it would be really weird for us. We're used to gravity really tugging on our feet, right? But imagine walking on the surface of an asteroid where you could potentially jump off by accident. That would be kind of a goofy experience, you know? Let's try doing some computations because I think that'll be good for you guys. I'm going to erase and I'm going to set up a problem. Does everyone have this? All right. Let's see if you can handle this one. Sample problem 1. Find the force of gravity between Earth and the moon. Oh, I wanted to tell you guys one other funny thing, or mention something. You know, some of my astrology worshiping friends, yes, I have them too. They sometimes say silly things like, oh, you know, well, that gravity exists, so when the planets, they can like send vibrations down and bop you off the head, and that's how the astrology works. They're gravitational forces. If you actually use the law of gravity to calculate the force of gravity between, say, you and the planet Jupiter, there's usually a stronger force of gravity between you and a nearby dump truck than there is between you and the planet Jupiter. But no one worries about dump trucks affecting their Tinder profiles. You know what I mean? So gravity is not going to be a solution to that problem. Why don't we find some things that do actually have a significant force of gravity? Earth and moon. We're going to need some values to start out. We're going to need to know the mass of Earth, which I know, thanks to Henry Cavendish, is 6 times 10 to the 24 kilograms. We're also going to need to know the mass of the moon. The mass of the moon is 7 times 10 to the 22 kilograms. And if we look up the distance between the two objects, it's about 384,000 kilometers. Okay. We know our law of gravitation. I'm going to write it over here in small letters. The force of gravity is big G times m1 times m2 over the distance squared. Notice that it's okay for me to put the big G up top, because if you multiply it or if you put it on the top fraction, it's the same thing. Okay, how should I start? What do you think, Tegan? What should I do?
Oh, yikes. Oh, not muted. Gosh darn it.
Yes. We heard that.
It's okay. I would have said it anyway, but
I guess,
right,
Tegan,
so,
what I'm asking you is, can I just plug these numbers in or what? Am I good to go? Is everything in the right form?
not yet.
Something needs to change. What is it?
Mhm.
I want to see if you guys can find it. One of these units is not okay because, as I mentioned earlier, Newton's law of gravity uses MKS units. Can you guys remind me what that means? What does MKS units mean?
Meter, kilogram, seconds.
So in that case, was that Mia who said that?
It was Mariah.
Oh, Mariah, sorry, you were a little off to the side. Mariah, what needs to change in that case?
The distance?
Yeah, we need to convert it from kilometers into
Meters?
yeah. Okay, so do you have the skills to do that?
I don't think so.
I think we do. What's your first step in dimensional analysis?
Write the units down.
Write the number down with its units. People always want to write the number down. Now you want to write the units down. Why can't we just get this party together and write down the number with its units? Okay.
Yes.
By the way, already did that. Step 1 complete. Okay, what's step 2?
You would do it times the conversion.
You do a
Is it?
division bar. And now what's step 3?
You would put the meters on top and then kilometers at the bottom. I
How
don't
do you know the kilometers had to be in the bottom? Just remind everyone.
just because they have to cancel each other out.
Like that, right? Boom, boom.
Yeah.
Okay. All right, and what's step 4?
Fill in the numbers.
Now we're going to need a conversion between meters and kilometers, which I think I gave you in one of your earlier pages. Look for the section called metric units of length. It should be in the beginning of this chapter, like probably Tuesday I gave it to you or something.
I don't think I can find it on my notes.
Who's got good notes? Now, last lecture on Tuesday, I remember starting the class off talking about, well, maybe, no, it's earlier back than that. It was just before I introduced an astronomical unit on like the second class. I had a little section called metric units of length, and I even had you put stars next to this conversion factor. Or maybe someone can just guess what it is.
I got it.
Is one, oh, go ahead.
Anyone?
All right. It's 1,000 meters over 1 kilogram.
Right, not kilogram, but
Kilometer.
right. So 1,000 meters is 1 kilometer. Guys, I was kind of hoping that you could even guess that, because remember a long time ago, I told you that kilo means 1,000 or 10 to the 3. So it's 10 to the 3 meters per kilometer. All right, whatever. Hey, Mariah, I bet you're so good at math that you could do this in your head without a calculator. Do you believe me?
I mean, I could try. Yeah.
How many zeros do we have here?
3,
How many zeros do you have there?
3.
So suppose I wanted to put this right into scientific notation. I could just write 384 times 10.
To the
Well,
6.
Yeah, and I don't even have to do anything. And I can even put it into my calculator, just like that. I want you guys to notice this important step. During the exam, many times I'll give you numbers that are not in the right units, and you need to know that the conversion needs to happen before you plug it into the equation. That's a step that when you're learning math, you don't always think about. You have to learn to do this, in other words. Now we're ready to solve for the force of gravity. So let's write it down. The force of gravity is, and I'm going to use blue for my units. Big G is always 7 times 10 to the minus 11, and its units are meters cubed per kilogram per second squared, times the mass of Earth, 6 times 10 to the 24, units are kilograms, times the mass of the moon, 7 times 10 to the 22, the units are kilograms, and divided by the distance in meters squared. And I want you all to pay very close attention to how I write this, because it matters. I'm going to open parentheses. I'm going to write 384 million meters, and then I close the parentheses and square it. Now, a lot of you are going to misunderstand why I did that. Many of you will think that the reason that I put those parentheses there will have something to do with your calculator. But it's actually not about the calculator at all. We're actually not going to punch those parentheses in our calculator. We don't need to. The reason why the parentheses are there is because this square not only distributes to the number itself, but the square also distributes to the units. And if you don't put the parentheses there, you can get confused about whether the square goes with the meters or the square goes with the number or both. This makes it absolutely clear. It's almost like a bookkeeping thing. And you probably think that's dumb. I don't care about that, but you will eventually. You want to learn a lesson from me, okay? All right, now it's time to punch this in. And for some of you who are doing this for the first time, this is going to seem wicked crazy, but it's actually not that big of a deal. Calculator's out. You got them? You got to punch with me or you're going to waste your time here. All right, I'll try to stand in such a way where you can see the equation and my calculator at the same time. All right, let's punch together. 7 exp negative key 11 times 6 exp 24 times 7 exp 22 divided by 384 exp6. Now we have to square that, so I'll direct my attention up here to the square key. Boom, that's the square. And now at the end, I hit equals.
Where is the square?
Right up there. Do you guys have this number?
And then it's equals.
And then after the square, you hit equals. Do you guys have this? Show me Mateus. Yep, Mateus has got it. Mariah's got it. Mia's got it. Philemon's got it. Tegan's got it. Anyone having trouble? I want to work with you.
I got caught up trying to find the negative key, and then I missed a step. I didn't get that number.
Sure, I'll work with you. Nick, what are you up to, Nick?
I just need to look behind you a second for the last number to
sure.
type in. Thank you.
Okay. I'm glad you're punching though, Nick.
7 exp.
Yeah, I got it.
11.
Good. Oh, using an unorthodox calculator, huh? As long as you're getting it, Nick, that's fine.
My calculator.
So here, Nick Souza,
Yeah.
7 exp. This is your negative key here,
Yep.
right? 11.
I found it eventually.
All right.
Yep.
Then you do times 6 exp
24
times
times
7 exp 22 divide by 384 exp6. Then you hit that square.
Yep.
And then equals. And this is what you should have.
Yeah, I have that now. Wait, so in this problem, where is the square? Maybe I just copied something down, the expo. Oh, okay, yep, I missed that too. I was wondering why you were doing that.
That's
okay.
very important.
Yeah, I just missed it.
Okay, did anyone else have trouble? Because I know it sucks to like say, hey, I'm not getting this right, but it's a good idea to do
It's
it.
tough. It's very dense
Kiana,
for
how'd
me.
you do?
I didn't get it the first time, but when you just went over it with Nick, I think I got it right?
Yes. What's your power?
31.
See, my power is
what?
20.
How did I get 31?
Can you just punch it in one more time for me, Kiana?
Yeah, I don't mind.
All right, how about Amy?
I got it, Brendan.
Okay, good. Yeah, I was looking for you, and Andrew. I couldn't find you in my little Hollywood square boxes. Oh, you're way over on the side. That's why. Okay, good. Andrew's got it.
Is it possible that we can do that again? Just so I don't.
I think that's
just
a great
look up.
idea. Yes, it is possible, and I think, especially for people watching later, that could be useful too. All right, I'm gonna let me get up my Logitech. What's happening is if I get too close to the screen, my camera isn't focusing. So just one sec, peoples. Let's do it. I think it's not a bad idea for us to all do it one more time. I just want to adjust my focus here. Patience. Okay, here we go. Let me focus to like 33. And now I can bring the calc nice and close without the glare. Okay, so let's just do it one more time for funs and giggles. big G is 7 exp negative 11 times 6 exp 24 times 7 exp 22. And now divide by, here we go, 384 exp6. Now we square it, and then we hit equals. That's what you should have. Whoever had the 31, did you fix that shit?
Yeah, I was going over it again, and then I went to go hit EXP, and I hit equals by
Oh.
accident.
All
Yeah.
right. Well, get it. We got to get it right. Okay. Now listen. Now there's several things about this. There's learning how to punch it into your calculator without screwing up. That takes a few go-throughs. Now we have to learn how to write this and simplify it. What should I write down as my final answer? Who knows?
I know.
All right. Tell me what to write, Andrew.
2 times 10 to the 20th newtons.
Amazing. I want to talk about what he just did there because he did two things that mattered very much to me. First of all, he rounded this number tastefully. He can see that 1.99 is so close to 2 that fuck it, we'll just call it 2. And all of that stuff is garbage. He keeps the 20 because that's sacred. And then he also includes his units of newtons. If you're wondering how he knew the answer was newtons, there's two ways to look at it. One is this is a force, and forces must be measured in newtons, so that's forced. But you can also see if you do a careful unit analysis that you will get units of newtons. For instance, meters squared cancel out with meters cubed to leave 1 meter. Kilogram cancels with 1 kilogram, leaving 1 kilogram, and seconds squared are still on the bottom. The result is meters times kilograms over seconds squared, and that's the units of newtons, okay? Okay, this is the force of gravity between Earth and Moon, and you'll notice it's a pretty big number, a lot bigger than the 10 newtons, which is the attractive force of a 1 kilogram mass on Earth. We're now going to try to compare it to another force of gravity. And part of the reason we're going to do that is I still don't trust that most of you can do this without my help. So I want to do another problem just like this, and I want to see who can get it right without any help from me, okay? Does everyone have this written down? I need to erase. Okay, doing it.
Set.
Oh, sorry, anyone?
All set.
All right. Okay, let's just do another problem like that because this is an important stepping stone for you guys for what we're doing today. So new problem, see if you can do this one without me. Find the force of gravity between the sun and the Earth. I'll give you some values. The mass of the sun is 2 times 10 to the 30 kilograms. Let me write this neatly and not sloppily. The mass of the Earth is still 6 times 10 to the 24 kilograms. The distance between them is 1 astronomical unit. And I'll remind you that 1 AU is 150 million kilometers. Okay, talk to me, peoples. What do I want to do?
Well, you don't need to change the distance.
Why not?
Because it's already in scientific notation.
No.
Not
Tegan, we got to
scientific.
clean up our speech. Scientific
Okay.
notation means this. Units
Okay.
do not go into scientific notation.
Okay.
However, Tegan, I want you to be careful. What does M KS stand for?
Meters, kilometers, seconds.
No.
Oh,
Meters.
gosh, wait a minute.
Kilograms. So
Oh,
this is something that happens is people think the K is for kilometers, but it's for kilograms. Excuse me. Ooh. K is for kilograms. So in fact, Tegan, your distance is not okay. What does your distance need to be in?
it needs to be in meters. Wait.
You said it right.
Yeah.
It needs to be in meters.
Mhm.
Okay, now it's time to do penance with me, mathematical penance. I need you to help me do some dimensional analysis and convert this into meters. So step
Okay.
1 is to write down the number with its units.
Mhm.
What is step 2?
Step 2 is,
Look it up if you can't remember. You should have it in the first day of your notes or second day of your notes or something. 4 steps of dimensional analysis. We need to memorize them.
you have to multiply.
By a division bar. Good.
Mhm.
What is step 3?
Write down the units.
Okay, so give me some units.
Kilometers on the bottom
Uh-huh.
and meters on top.
Good. Step 4 is to put the numbers in second. So what's my conversion from kilometers to meters?
1,000 meters per kilometer.
Excellent. And now for your final cool guy step, let's do this in our head. You've got 6 zeros and you've got 3 zeros. Put them together, and how many zeros do you have?
9.
So that's 150 times 10 to the 9 meters. Bonus points if you know what 10 to the 9 means. How big is 10 to the 9? That's like a
Billion?
A billion. Good. So 150 billion meters. Now we can set her up. The force of gravity between sun and earth, I'm going to put a little subscript there so I can remember what I'm doing, is big G, 7 times 10 to the negative 11. Units are meters cubed per kilogram per second squared, times the mass of the sun, 2 times 10 to the 30 kilograms, times the mass of Earth, 6 times 10 to the 24 kilograms, and divided by 150 billion meters squared. Okay, time to impress me, class. Show me that you can do this computation without my help and get the right answer and round it and everything. Just see if you can do it. And do it quickly because I've got a few more topics to cover before office hours. I've got to squeeze a lot into our last half hour here. Let me get a drink while you guys punch that in. All right. I'm curious. I got more iced tea. I'm curious to see what's what and who got this right. Mateus and Andrew, you guys are veterans of my 1010 class. Did you get an answer? Mateus
I
says
did.
yes. All right, so you guys hold back because you know you have a little more experience. I want to hear what these guys are doing. So Mia, Philemon, Tegan, Amy, show me what you got, Amy. Amy, that looks good. It's a little hard to see, but I think, yep, Tegan, yes. Mia, yes. How about Philemon? Philemon, yes. Can you read that out, what you have, Philemon? Because I think I like the way you did it there. What'd you get, Philemon, for your final answer?
4 times 10 to the 22nd Newton.
Excellent. And I like your bold rounding style, sir. You have bold rounding style.
Thank you.
Okay. So as most of you realize now, he rounded that from, let me see, I can do this pretty quick, times 2exp30 times 6exp24. Damn, I'm so fast. Okay. So just to show the class who's watching the video later, he rounded from 3.7 times 10 to the 22 right up to 4, which is what I wanted.
That was pretty impressive.
Yeah. Oh, I got some quick draw fingers here. Now listen, and you guys will too. By the end of this class, you're going to be just as fast as me. You'll see. Now, Philemon, do you think the gravity, what did we learn here? Is the force of gravity between the sun and the earth greater or weaker than the force of gravity between the moon and the earth? I was asking you, Philemon, but if you're unsure, in other words, Philemon, we just got 2 answers in the last couple minutes.
Yeah.
This is our force of gravity between sun and earth. A moment or two ago, we got a force of gravity between moon and earth. Which one's bigger?
I think the
Why
force
don't we write them down next to each other? What did you get for the moon earth gravity?
2 times 10 to the 20th Newton. Wasn't that? So was it?
Yep. And I want to make sure that you guys know how to interpret this, okay? So this is earth and moon. So first, Philemon, which of these numbers is bigger?
The sun.
The sun earth. Because the most important thing is the power is bigger. That's the first place you check. You look at the power first. If this power is bigger than that one, this is bigger, okay? You can also look at the lead digit, but that matters less. Okay, now here's a game that we're going to play all the time, Philemon, and I want you to start showing the class how to do this. Once we have these 2 answers, I'll oftentimes ask a follow-up question, which goes like this. Compare the force of gravity between sun, earth, and moon, earth. And I don't know if I said this before, but compare means something very particular in this class. When we write compare, that is code word for take the ratio. That's how big boys and big girls compare, okay? So Philemon, we're going to do this without any calculator, okay? We're going to divide the big guy by the small guy this time. So we'll have 4 times 10 to the 22 newtons divided by 2 times 10 to the 20 newtons. And let's see if we can figure out how to do this without a calculator, Philemon. The first thing we do is we realize that we have newtons on top and bottom, and we cancel them. Boom, boom. The second thing we do is we deal with our power. We subtract the powers. So we have times 10 to the what power?
Second.
Okay. And now we divide the lead digits 4 over 2. 2. And Philemon, what is 2 times 10 to the 2? What does that mean?
2 times 200.
Good. And now, Philemon, for the final act, what does the 200 mean? What does 200 mean?
The gravitational pull, right? Or
keep going. The gravitational pull of do we need to phone a friend?
Yeah, sun of the Earth.
The sun-Earth gravity is, keep going.
The sun-Earth gravity is oh Jesus, hold on.
We're just trying to figure out, okay, Philemon, can I make this easier for you for a second?
Yes.
Philemon, let's just take a little kid's break, okay? Listen, Philemon, suppose I have 10 cookies. And suppose you have 5 cookies. And then we compare cookies. 10 cookies over 5 cookies is 2. what does 2 mean in that case?
You have 2 times more.
Cookies than you do.
Yeah.
So now it's the same thing over here. It's just not cookies, it's newtons.
Oh,
What
so
does the 200 mean?
200 times more. The sun pulls 200 times more than the Earth?
The sun-Earth, let's say this better. The sun-Earth gravity is 200 times stronger than the moon-Earth gravity. But you could think of it as, I don't like to say the sun tugs 200 times more than the moon because Earth is also contributing to the tugging. So that's a little weird. But we would say the sun-Earth gravity is 200 times stronger than the Earth-moon gravity. And that's how we compare, and that's what it means, 200 times stronger. Now, Philemon, we live in the ocean state, right?
Mm-hmm. Yes.
And that means we're familiar with the changing cycles of the bay. We have tidal changes. I can see them down in the Providence River there when I take a walk after class every day. What causes the tidal changes in the Narragansett Bay? What's the cause of tides on Earth?
The gravitational pull.
The gravitational pull of what?
The moon, right?
The moon. So who just said that?
I did.
Wait, who's I? I'm looking for your.
Kiana.
Oh, Kiana, there you are. Sorry, you were over on the far edge of the box. Okay. Kiana, I've heard that before too. In fact, when I go along the East Bay bike path during the springtime, I have like little tidal estuary information signs telling me about how the moon causes tidal changes in Narragansett Bay. But Philemon and Kiana, I've got a question for you. Why is the moon causing tides when we just calculated that the sun-Earth gravity is 200 times stronger than the Earth-moon gravity? Why is the moon causing tides when its gravity is 200 times weaker than the sun's? Doesn't that seem weird?
Because it's closer to Earth?
You could say that, but my contrary point would be this. Didn't we include distance in our calculation? Because you can say because it's closer, but look, we plugged in the distance between Earth and the moon, and we also plugged in distance between Earth and the sun. And even though the moon was closer, the sun's gravity was still stronger because the mass of the sun is 2 times 10 to the 30 kilograms. James, what are you thinking?
Could it be because it rotates around us, and rather than the sun rotating around us, we rotate around that? Like,
the rotation stuff is a little bit complicated. It turns out that who is rotating who is kind of a matter of perspective and what we call reference frame in physics. One way to think about things, James, is that the Earth moves around the moon. Another way to think about things is that the Earth-Moon system orbit a common center of mass. And then that system of rotation also orbits around the sun. So everyone's kind of orbiting everyone. And while circular orbits do create weird effects, it's just not the right answer here. In fact, I kind of set you guys up for a fail. The answer is really tricky. It's very subtle, and you have to learn. We have to do a little module about the tidal force, okay? So the reason I asked you that question was to get you thinking, what's going on there? It turns out that distance is a part of it, but it's just a little more complicated than simply distance. So let's take some notes on this. I'm going to erase, and we're going to have a lesson on the so-called tidal force. This is a big subject in astronomy and physics. Also, one of our homework questions today is on tides, which is why we're covering this. Let's do a module called the tidal force. Okay, I'm going to write down a couple of statements that are true to help you understand what I'm saying here. The first statement is this: yes, tides are caused by gravity. That is a true statement. But here's the difference. The so-called tidal force is not the same as the gravitational force. They're different. There is something called the tidal force, which is caused by gravity, but the tidal force is not the same as the gravitational force. Sorry, I ran out of room there. There is a distinct difference, and here it is. The tidal force is what we would call in physics a differential force. And I'm going to underline that because that's a buzz phrase. The tidal force is a differential force caused by gravity acting over an extended body. It's a differential force caused by gravity acting over an extended body. And I'm going to flush that out even more, okay? In other words, the tidal force is a delta force. You guys have seen me use this symbol in my last lecture. What does delta mean, my close paying attention friends?
Change in.
Change in. So it means a difference in force between the force of gravity acting on the front of a body minus the force of gravity acting on the back of the body. And this happens when you have large extended objects like planets and moons. The planets and moons are sometimes so big that gravity varies from the front to the back. And believe it or not, the subtraction of force is different than the force itself. It's a difference in force. It's a change. In fact, here's another way to say it. It's a change in force. In fact, what I really want to do is I want to use a much more fancy term, but I'm afraid it won't be fair to you. Has anyone out there in the studio audience been exposed to calculus? I'm not saying are you good at calculus. I'm just saying, have you ever tried to take a calculus class or something?
I have.
Oh, Nick has. Okay. So this will be just for Nick's sake, but I'm going to tantalize you guys with it just for fun. In calculus, we call it the derivative of force. It's still the same as a change, but it's a little more subtle. The tidal force is a derivative of force. And here's what's interesting. When you take the derivative, let me put it into non-mathematical terms. Do you guys know what a gradient is? Let's show a picture. And gradients can take many different forms, but you guys might call it a fade. Let's type in black to white gradient and see what happens. Gradients can be mathematical, or they can be a color gradient, or if you get a buzz cut and you get a fade, that's kind of a gradient sometimes. A gradient just means you have a change in values, and this could be a change in pixel intensity. From the front side of the screen, you could have like 100% brightness, and it slowly varies to 0% brightness. In the same way that this is a gradual gradient or a fade from white to black, if you have an extended astronomical object, you can have a gradient of forces from the front to the back of the body. And here's where I'm going to use a little picture time to explain what I mean by that. Let me share, I'm going to try this out, my whiteboard. When we calculated a moment ago the force of gravity between the sun and the Earth, we basically did this. We assumed that we had a little mini point particle called the sun, and we assumed that we had a little mini point particle called the Earth. And then we assumed that it was just 1 AU between these two little points, and we calculated the gravity between sun and Earth. And that is a pretty good approximation of how gravity works, and the number that we got is reasonable. But now let's look at the reality a little more closely. Let's look at it with the Earth and the moon. Oops, sorry, Control Z. Earth, as you know, is an extended body. And if the radius of Earth is 6,400 kilometers, that means that the radius of Earth front to back, 6,400 times 2 is 12,800 kilometers. Okay, cool. Now let's throw in a moon. We'll do orange for the moon. We're going to make an orange moon. So here comes the moon. And the moon is also an extended body. And now let's talk about the distance between center to center, Earth and moon. So if I go from the center of the Earth to the center of the moon, we know that that distance is 384,000 kilometers. Okay, now class, think about this. 12,800 kilometers is a significant percentage, well, a non-zero percentage of 384,000 kilometers. Can you guys do that for me? What percentage of this distance is this distance? Let's take out our calculators and let's do 12,800 kilometers. And I want you to divide it by 384,000 kilometers and tell me what you get.
3%, 3.3.
Good.
3 repeating.
For the benefit of those who are maybe not so great at the math, if that was James that I just heard there, I want to point out that what he actually got on his calculator was probably 0.03. And it sounds like he's got some math chops there. So he quickly recognized that that's the same as 3%. I want you guys to recognize that as well. Okay. So according to our analysis, this means the front side of Earth is 3% closer to the moon than the back side of Earth. And think about what happens when you account for distance and gravity. Let's imagine that I could invent me a giant planetary-sized cheese grater. And I could take a slice of Earth cheese somewhere up near the front of Earth. This little wedge of rock and metals would have a force of gravity on it, and the moon would be tugging on that force. That's the force on the front of the moon. So we'll call it force on the front. Okay. And now I can take an identical slice of Earth cheese somewhere near the back. And I'm going to do it in such a way that this thin little slice has the exact same mass as the front slice. Now recognize that there will be a force of gravity that the moon exerts on the back of Earth. And obviously, the force on the front of the slice of Earth will be stronger than the slice. Oh, God, let me say this better here. The force that the moon tugs on the front slice will be stronger than the force the moon tugs on the back slice, right? Because the front slice is 3% closer to the moon. Will it be intense? No, it'll be subtle, but it will be significant. Okay, I'm getting sick of drawing on this crappy whiteboard. So let's try it over here with some cartoon numbers. Does everyone have this?
Oh, I'm not done.
Oh, okay. I'm going to add one thing here. When you take the change in force, the tidal force, and this is for the calculus fellow back there, but it's also for you guys. Unlike gravity, which is proportional to 1 over the distance squared, the tidal force famously is proportional to 1 over the distance cubed. It's so weird. Even though this is still a change in gravity, its distance dependence is weirder, meaning it's really strong when you're close and it gets weaker when you're farther away. Andy, let me know when you're done with that.
This is also the reason that Europa's moon is not, or Europa's not fully frozen, right?
So the cracks in Europa's surface, this is a 10-10 question really, but we can talk about it. We do believe that there are definitely tidal forces that are exerted on the inner moon of Io. Europa is a little bit further away. So remember that this 1 over d cubed dependency for Europa means the tidal force is falling off really fast. By the time you get out to Europa, there probably are tidal forces, but they're much weaker. Now, the answer as to what causes those cracks in the surface of Europa's ice surface, it could be partially tidal forces, but it's also possible that there's underwater, that the tidal forces are actually affecting the rock underneath the planet. They're heating up some geological fissures, which then warm the water, and the water adds to the lubrication. So I would just want to be careful there, because I don't know if I'd want to say the tidal forces are cracking the ice. It could be a little bit more complex.
It's more of like a push and pull on like the core, right? And it's that like tiny bit of stress that releases heat.
So on Earth, for instance, our plate tectonics are caused by internal heat of the planet. So the tidal forces are probably adding a bit of internal heat, and then the internal heat manifests itself as cracks in the ice. I just wanted to get particular about that. Just to make sure that you guys understand, let's draw a little cartoon of this. And I have other stuff to do before we end class today. Oh God, I'm running out of time. Okay, so you know what? I have more to say about the tides. Okay, I'm gonna do it anyways. Look, here's the Earth and here's the moon. Let's imagine on the front side of Earth, a little front slice gets tugged on by 40 newtons. This is a totally made up number, but it's the cartoon that matters here. Let's say the back side of Earth gets tugged on by 20 newtons. I could then say that there is a tidal force on Earth, which is the difference between the front minus the back force, which is 40 newtons minus 20 newtons, is a 20 Newton, and the word is differential. So now let's take a look at how tides work with a slideshow here. Oops, sorry, this is not what I want. Share screen to the slideshow, and boom. So the gradient of force is actually acting across the entire body of Earth. In addition to water tides bulging the oceans in the direction of the moon, and keep this in mind, it also bulges, we get a second high tide opposite the direction of the moon. There's two ways to understand that. One is to think about it from an Earth reference frame. The 20 Newton differential makes Earth feel like it's being pulled apart, like two kids fighting over a teddy bear. It's being yanked apart side to side. If that's not helpful to you, you can also think of the front side of Earth getting the hardest tug, and you can think of the center of Earth getting the second hardest tug and being pulled away from the backside. Not only does Earth experience water tides, the atmosphere of Earth also bulges in the direction of the moon. And even more crazy, and related to, if that was James's discussion of Europa, the actual rock that you stand on gets deformed by about 3 centimeters each day in the direction of the moon. And on Earth, that's not enough to heat up the Earth, but you're literally bulging the rock mass underneath your feet. In the case of Jupiter and its moon Europa, and especially in its moon Io, Jupiter is such a massive planet that it actually warps and whoopies the planet and heats it up like you're kneading up a pizza dough or something. So, so tidal forces do cause planets to heat up moons within our. Tidal forces are wild. They do all kinds of crazy things. The thing that I wanted to point out to you is, let's say you were a pesky student and you wanted to ask me some pesky questions. And you'd want to say, you know what, Brendan? Okay, I hear you on this differential force, but didn't we just calculate the sun's gravity as being 200 times greater? Why shouldn't this also be happening with the sun? I would say, yes, it is, but think about this. The Earth's body, 12,800 kilometers, is a much smaller fraction of the distance to the sun. The distance to the sun of 1 AU is 150 million kilometers. And if you do that as a percentage, watch this. So 12,800 divided by 150 million, we're talking 9 times 10 to the minus 5, which is the same as 9 times 10 to the minus 3%. So we would say that as 9 thousandths of 1%. So it doesn't matter if the sun is tugging stronger on Earth, because let's say the front side gets a tug of, I don't know, 400 newtons. The percentage variation across the body of Earth is so tiny that the backside of the Earth will only get tugged on by 399 newtons. So the tidal force that the sun exerts on the Earth is 400 newtons minus 399 newtons equals only 1 Newton differential. Thus, it's possible to say two things that sound contradictory but are not. The sun tugs on the Earth stronger than the moon at all points, but the difference in force between the front and the back is stronger from the moon than it is from the sun. See what I mean? The tidal force isn't the same as how strong gravity is. It's about the variation or the gradient in force. In fact, as any good cawhogger or fisherman in Rhode Island knows, the sun does affect tides. Twice a month, we get really powerful tides at new moon and full moon because the gravity of the sun augments the moon a little bit, and you get very potent spring tides. Likewise, twice a month, when the moon is perpendicular to the sun at first and third quarter, the sun offsets the tidal force, and you get weaker than average tides called neap tides. And fishermen are well aware of this because they're out in the sea every day and they're watching the level of the water rise against the rocks. In other places in the solar system, actually, we're not interested in the solar system in this class. We're interested in going out into the galaxy. There are places where tidal forces can become so bonkers. For instance, in the classic case of a black hole is literally a microscopic point particle with shitloads of mass. So what happens is, as you get close to a black hole, even if you're something small like a 2-meter person, 2 meters is infinitely larger than a single point particle. So getting closer and closer to black holes becomes dangerous because the difference in force between the front side of your body and the back side of your body can be so immense that it can just rip a person apart. I think Neil deGrasse Tyson calls it spaghettification. You'll get stretched out into a puddle of molecules. And literally, stars that get too close to a black hole can have tidal forces that will disrupt them into a ring of hot plasma that then orbits the black hole. Most black holes actually have chewed up star bits circling around them in a form of hot gas. I'll be teaching you about that in good time as well. Okay, wow, I really went nuts on the tides there. Okay. With the few seconds I have left, I want to talk to you guys about another important equation that's part of this week's homework. And I'd normally like to introduce it with like a little more storytelling, but I don't have time to do that. As you remember, Newton made 2 discoveries that are important to us this week. He discovered the laws of motion, which tell us how forces cause things to move. So this is his laws of motion. He also discovered a particular force, the law of gravitation. And these 2 accomplishments were already a tremendous achievement for any scientist. Law of gravitation. Newton being Newton, he did not stop there. He then took these 2 things and started combining them so that he could analyze the orbits of planets and stars. And because he had learned to think of the force by studying Johannes Kepler, what he was interested in doing was combining this and this to be able to do a new analysis of Kepler's laws. You might think of it as Kepler's laws improved. For instance, do you guys remember what Kepler's first law of planetary motion was? What was the first law of planetary motion that Kepler discovered? I'll give you a hint if you can't.
The law of ellipse.
And what does the law of ellipses state?
A planet orbits the sun on an ellipse with the sun located at the focus point.
Right. Now, as far as you were concerned, if you were Kepler, the only thing that could orbit the sun would be planets, and the sun would be fixed perfectly at the focus point of the solar system. But Newton could see that if mass was the cause of it, there could be other stars and other planetary systems which also had mass. And what if instead of a little planet and a big star, you had like 2 stars orbiting each other? Or what if you had like a binary planet system? How would the ellipses work then? Newton already realized that Kepler's laws would not work for the moons of Jupiter, and he was very concerned about that. And he realized that Kepler did not have the concept of gravity, and he didn't know that mass was involved. So Kepler's versions of the orbital formulas, they only work for planets going around the sun, but they don't work in any other case. Newton realized that he had to improve Kepler's laws, and he did so with his law of gravity. Now, I want to introduce a formula that's going to be very important in this class, and I'm sorry I'm squeezing it into our last few moments, but it's part of our homework today, so we should introduce it now. I want to make a contrast between Kepler's third law of planetary motion. You guys will remember that it was p squared equals a cubed. Let's see what you remember. What does p stand for?
Perihelion.
No, it is not perihelion. We use peri for perihelion. P is something different, Andrew.
It's orbital period, right?
Yep. It's the orbital period. And what units do we use?
Years.
Good. How about A?
A is the semi-major axis.
And just to keep things simple today, I'm just going to call it the distance, like the distance between the two, between the planet and the sun. And I want to remind you that that's measured in AU. But here's the thing about Kepler's laws, and I'm telling you stuff that's really important for you on the test, okay? This only works for orbits that go around the sun, or, I have to be honest, a star of equal mass, it will also work. Sorry. In other words, I want to be really explicit about this. This will work for planets going around the sun. This will work for comets that go around the sun. But this will not work for moons because moons do not orbit the sun. It will not work for binary stars and other things like that because they don't have the same mass as the sun. Newton invented a better version of this formula that will cover all the checkboxes and will work for any two orbiting masses. That's because it accounts for the differences in gravity of the stars. But of course, that formula is a little more complicated. Let me introduce to you Newton's version of Kepler's third law. Now, every time I want to say this, that's a lot of words, Newton's version of Kepler's third law. So forgive me, but sometimes I'm just going to call this NK3. That's my nickname for it. I don't know if other astronomers do that. I call it NK3. And it looks similar, but there's more stuff and the units are different. P squared is equal to 4 times pi squared times a cubed divided by big G times, open parentheses, the sum of the two masses. This is a legendary formula that is so important to astronomers. Once again, this works for every orbit. Doesn't matter what it is, planet, star, quasar, whatever. There are some differences in the units. P must be measured in seconds. A must be measured in meters. And of course, the masses must be measured in kilograms. In other words, this equation, to say it like a scientist, is an MKS equation. And with that, I'm out of time. Okay. Obviously, it's not enough to introduce a crazy thing like this. We then have to practice it. Unfortunately, time is a factor in your lives as well as mine, and we just hit 1:30, which is technically the end of lecture. My take on it is we're going to use this in today's homework session, right? So the practice will be the homework as we do it together. Is that acceptable to everyone? Otherwise, we're going to tack another 15 or 20 minutes onto this day, which I don't think anyone wants,
That's fine.
right?
Fine with me.
That's. Could you move the board down a little bit?
Sorry, like that?
Yes, thank you.
So at this point, as we always do, you guys have just had an hour and a half of listening to me talk, which I'm sure is exhausting in its own way. We should take a little 15-minute tea break so I can drink some tea and chill and you can chill. And then we'll do homework 3 together. Is that correct? All right. Unfortunately, guys, just like last week, today's homework, because it involves some crunchy stuff, it's going to be a little intense. So steel your nerves. But I will go through it as quickly and as efficiently as I can. So I'm going to pause the recording. I'm going to take a little break and have a snack. And I'll see you guys at 1:45-ish or around there.
So it's
Okay, friends, I'm ready to get back at it if you are. Should we crush this thing or what? Someone do me a favor and open up that homework, and if you can all get out the questions so I can ask you guys to take turns reading it. Just gonna clean things up a bit. I'm just making dry erase mud over here. All right, that'll have to do. Let's format our homework in the usual manner. At the top, your name, first and last name, please. No Bobby J or Mickey Joe, give me your first and last name so I can keep track of you. Always remind ourselves that we are in Astronomy 1020. Please put your section down, whatever the hell that is. Let's make a note that this is homework number 3. The questions are from the book's chapter 4. Who can give me the numbers?
I got you.
45. 47. 56. 57 and 58.
Excellent. Let me just check and see how many people we got in the house right now. Okay, we got a few folks. Remember, interacting with me is part of the price that you guys have to pay, sandwich or not, Mia. Because I have these videos already recorded, but I want you guys to interface with me a little bit to make it worth my time. Otherwise, I can just show you the pre-recorded ones from last semester. Okay, so Mia, you seem like, or I'm sorry, Andrew, would you like to start us off, Andrew, by reading us chapter 4, number 45?
Yeah. What is it? Chapter 4, 45?
Yeah, and don't forget, I like the titles too.
All right. Oh, it's blocking me. Oh, there's an error.
Glitch board, as I like to call it, right?
Yeah, it's.
Glitch
All
board.
right, I'm gonna restart this page and see what it does. Maybe because I haven't touched it a little bit.
Sometimes if you right-click the PDF, it'll open in a new tab.
Yeah, I got it. I got it now.
Okay.
All right, so what one is it?
45.
Oh yeah, 45. The gravitational law. How does quadrupling the distance between two objects affect the gravitational force between them? So that's for A.
Okay. Before we begin, let me say that this is an investigation into the Newtonian version of Newton's law of gravitation. That is, we're going to explore that proportionality symbol that I taught you about today. And as Newton wrote, the force of gravity is proportional to the product of their masses and inversely proportional to the square of the distance. And I did my best to train you on this method today. Part A, Andrew said, suppose what?
The distance between two objects affect the gravitational force between them.
Wait a minute, I think you missed something, buddy. Let me open this up here.
Did I?
Where's glitch board at here? Get out of here. 1020. Homework. Homework 3. Whoop. Chapter 4, PDF, open new tab. Sorry, I don't know if this is the important word. How does quadrupling the distance between two objects?
All right.
How does quadrupling? Quadrupling means increase by a factor of 4. Okay, let's start off by writing our proportionality argument. Class, what am I supposed to write here? Force is proportional to what? Too bad Philemon's not here. He seemed to have a pretty good grasp on that.
Notice that one more time. I was just writing stuff down.
Sure. The answer to this problem is not complicated. I want to make sure that you guys know how to set up a proportionality argument. I want you to be able to wield this sword in the proper way. I would like to start by writing force is proportional to, and which of these variables do I want to include here? Like, what do I want to write?
It would be, yeah, I have all the notes here.
First, I just want to write it in terms of algebra. I don't want to do any numbers yet. I just want to write the form. Does that make sense?
Yeah. I have the F is proportional to the M1 times M2 over D, which is what you already have there.
D squared. But here
squared,
we're not,
yeah, I'm sorry.
We're not varying all of these factors. We're only varying
mass. Is it mass times acceleration? Is that what you're looking for?
No, that's a completely different equation. We're dealing with this.
That's
equation.
a lot of never mind. I'm sorry.
See,
yeah, I have nothing for
I'm
you.
worried that you guys don't know how to set this up. Does anyone understand what I'm trying to get at here?
I feel like it kind of just went like really fast.
Yeah, that's the problem. It always has to go fast. What do I write? Anyone else?
Force is proportional to 1 over d to the 4th.
No.
Oh, no, wait, I'm sorry.
The
1 over
d might vary by 4, but the square is sacred, right?
1 over 4 squared.
That's, hold on, but I don't want you to substitute it in yet, Mia. I just wanted you to write it symbolically. We have to learn how to talk to each other. This is always the difficulty. Well, all right, let me explain what I wanted you to do. I wanted you to recognize that mass 1 and mass 2 are not changing in this problem. The only thing that's changing is the distance. So I wanted you to start, Mia. Where's your little face? Let me find your little face. Okay, there you are. I wanted you to say, Brendan, force is proportional to 1 over the distance squared. Basically, I wanted you to recognize that we can ignore the masses because they are not changing. Does that make sense? Now I want you to substitute in the factor by which the distance varies. And by the way, you can't change that too, Mia, because nature herself invented that too. You can't mess with nature, okay? So I would write what next? Now tell me what you said.
Now put 1/4 squared.
Good. Now that we have an expression that we can evaluate, we can transition from proportionality to a direct equals. And what's on the other side of that equals?
16 or 1/16.
1/16. What is the meaning of 1/16? Mia.
I hit you with stuff. So the force is no. I'm stuck. Would it be
You had it. You had it.
1/4 of the original force?
1/4. That's not what you have there.
1/16. 16th the original force greater.
Okay, can you now say that in a sentence that you've got the
Sorry.
right idea, but just say it smoothly now.
So
let me start you off. The new force is?
The new force is 1/16 greater than the original force.
Thank you. Thank you. The new force is 1/16 the original force. Or, put more simply, 16 times weaker. Okay. A few bumps in the road there, but we're getting it, I think. Write that down, and then I got to erase here. And I'm erasing now. Okay, Andrew, what does part B ask?
All right. Suppose the sun were somehow replaced by a star with twice as much mass. What would happen to the gravitational force between Earth and the sun?
Okay. We've doubled the mass of the sun. Nick, how will I write my proportionality arguments? Nick Souza. Force is proportional to what?
Go back in my notes here.
Or you could switch the computer off and use the force loop. Just use the force.
Oh yeah, so it would be mass 1 would be the sun.
Right. And so force is proportional to mass 1. Do I need anything else?
Mass 2 would be, I don't remember the second part of the question. I was just writing stuff down.
Okay.
It was 2 times greater than what?
The question was, what if we doubled the mass of the sun? How would that affect the force of gravity between the Earth and the sun?
So would M2 be it was the Earth and the sun, or the moon and the sun? I'm sorry.
Earth and the sun. In this case, so, M1 would be the sun, and M2 would be the Earth. But
correct.
We're not varying the mass of the Earth. That's staying the same.
I'm stuck. I'm gonna have to phone a friend on this one.
Okay, let's phone a friend. Does anyone? Let's just see if anyone understands me here, because I'm starting to worry that no one does.
To be completely honest, I'm pretty lost with this one. With this.
Okay, so let's fix that. This is actually not a complicated thing. I just need to figure out where we're not communicating properly to each other. Somehow I have not explained something. In a proportion, all right, so maybe let's take a step back. What the F am I trying to do? I'm trying to answer the question, if I vary one of these properties or one or more of these properties, how will the force change? For instance, I want to be able to say something like, if I multiply the mass by 5, the force will change by this many times. If I increase the distance by 20 times, the force will change by that many times. That's what the proportionality does. The thing that seems so simple to me, but somehow so complicated to you guys, is you want to rewrite this when you start, but you only want to include the variables that are changing. And somehow you guys can't seem to ignore the ones that aren't changing, but only include the ones that are.
When I look at this, sorry, when I look at this equation, I'm just trying to think about what to plug in. Where?
You're already missing the goddamn point. You're not ready for plug-in time yet. You're not ready for plug-in time until you can stop and say which letters are changing and which letters are the same. So let's go through this problem. Assume that we're calculating the force of gravity between the sun and the earth. M1 represents what? You're muted.
The sun.
The sun.
M2 represents what?
The earth.
And D represents what?
The distance squared.
The distance between the earth and the sun is what D represents.
Correct.
In this situation, which of the variables are we altering?
Distance?
God, no.
M1, because it's the sun.
Yes, thank you. We're not changing the distance. We're not altering the mass of Earth. We're just altering the sun. So you can ignore everything except M1 because only the mass of the sun is changing. So force is proportional to one of the masses. That's it. And then we plug in what factor we're changing the mass by. A factor of 2. And that's it. We're done. But what does this mean? What's the answer to the question? Let me start you off.
I know.
Yeah?
All right, so the new force is 2 times stronger.
Yeah. The new force is 2 times stronger. That's it. All I wanted you guys to do was to recognize that only one of the masses is changing. So force is directly proportional to one of the masses. Double one mass, you double the force. If you triple the mass of the sun, you triple the force. If you double the mass of Earth, you double the force. That's all I'm trying to say. All right, let's see if we got it now. Let's go on to part C. Let's see if you guys if I've made any headway with you. Andrew, what's part C ask?
All right, so suppose Earth were moved to 1/3 of its current distance from the sun. What would happen to the gravitational force between Earth and the sun?
Okay, someone in the background in the troll audience, I could hear your voice and you said, to be honest, Brendan, I'm not sure if I really follow what's going on. Who was that?
Sabrina.
Sabrina.
Yeah.
Sabrina, the way that you overcome this is you have to play with me here and you have to bash your head. Oh, there you are. Hi.
Hi.
Sabrina, let's you and I bash our heads against this wall because that's the only way to learn this stuff, okay? So let's see if we can get you to understand.
All right.
In this problem, we're calculating the force between Earth, the sun, and their distance between them. But what we're doing is we're changing the distance to 1/3 the original distance. I want to start by writing my proportionality argument. Force is proportional to, what do you think I should write down? What's your best guess? Just letters now, no numbers.
The distance?
Okay, when you say the distance, that's how I interpret that.
So distance squared?
You definitely need to square it, but you're still not right yet. You're getting closer. Yes, you have to keep the square, but I still object to that for one reason. What's wrong?
Does it have anything to do with the sun? I mean the Earth?
No. Just about looking at this equation and keeping it the same.
Okay.
First, I said force is proportional to, and you said the distance. So I wrote down D, and I was very unhappy. Then you said distance squared. I got a little more happy, but I still wasn't totally happy. What do you need to do to make me totally happy here? Does anyone besides Sabrina understand?
Yeah.
Go ahead.
I think so.
Tell me.
Are you talking to me?
I'm talking to anyone at this point.
Okay.
I'm just, see, here's
Is
how
it
this,
going to be 1/3 squared?
no, Mateus, I don't want you to put in any numbers yet.
Got it. So it's going to be 1/d squared.
Thank you.
Because that's what you're looking for, the distance.
That's what I want. I just want to make sure that you guys understand that D is in the bottom of the equation. And you cannot mess with that, Sabrina, right?
Okay.
Sabrina, it's
Yep.
not the same to say D squared when D squared is in the bottom. It probably doesn't matter to you, but it matters to me a lot whether something is in the top or the bottom. And I want you to impress that upon you.
And that's pretty much what we did on part A too, where we
Well, right. So I thought you would use that. Okay, fine. But
okay.
You see now, all we did is we neglected these two masses because they're not changing, but you leave D in the bottom and you leave the square with the D. Do you see?
Yep.
This is very important. Okay, now let's proceed. Now we can write the proportionality again, and we will now substitute the factor by which D changes. What factor is D changing by?
1/3 or.
So watch how I do this. We have to be very careful here. 1/parentheses 1/3 squared. We need to put that in parentheses so we don't mess up our maths. Now we can turn this into an equality. And Sabrina, let's see if you can evaluate this from your old math days there. Take the square, distribute it top and bottom. What's 1 squared? Well, first of all, we have to do 1/. You have to distribute your square to the 1 and to the 3. So what is 1 squared?
Is it 2/6?
Nope. Let's just do it one step at a time. Do you know what 1 squared is? 1 squared means 1 times 1. Right?
Mm-hmm.
So what's the 1 squared?
1 times 1.
So, all right, maybe I'm losing you here.
Yeah.
If you have something in parentheses, 1/3, you are obligated, if you're going to square that.
So it's 1/3 times 1/3 or something like that?
No.
Okay.
You're obligated to distribute the square to the top and to the bottom. So in other words, 1 squared over 3 squared. I was thinking we could take it in slow, easy stages. First, let's evaluate 1 squared. 1 times 1 is
1.
Okay. And
so
then
1
what is 3 times 3?
9.
Okay. So you have 1/1/9. That's what you have. When you distribute the square, you get 1 divided by 1 squared, which is 1, and 3 squared, which is 9. And what does that equal to? How do we do this? I taught you guys a lesson about fractions in our last lecture. The 9 is the bottom of the bottom, right? I might as well be just conducting this in Chinese. No one understands me. No one understands me. I want to die. Okay.
I'm gonna have to honestly review this whole thing over again. Like
it's okay. You know what, Sabrina? The way you learn, you feel. I've been in your situation before because I've taken so many physics classes. And what physics classes do is they just make you feel constantly dumb, like you don't know what's going on. And at first you think it's your fault. You think, oh, I've got to like go over all the. That's not how you learn. The way you learn is you just launch just over the ramp, head first into the bushes, and you scramble around, and then somehow you figure out what's going on. So it's okay to be confused. You just have to keep pushing forward, and then you'll figure it out. Can anyone out there tell me what 1 divided by 1/9 is?
9.
That's right. Okay, so what do I want to say? The new force is
9 times greater
yes.
than the original force.
That's right. So weirdly, if you move Earth to 1/3 the distance, if you shrink the distance by a factor of 3, the force goes up 9 times because of that square. Okay, that was a little bit of an adventure. The problem is you guys have never really used a proportionality symbol before, so it doesn't make any sense to you. Professional scientists use it all the time to great effect. And if you want to learn to think a little bit like a scientist so you can understand how we think, you got to learn about this, okay? All right, let's move on. That covers number 45. I'm going to erase. Here I go. Okay, Sabrina, since I've got your attention, will you read us number 47?
Hold on.
Toothpicks and dry erase markers, it turns out they don't go so well together. Because pretty soon you're chewing on this.
Hold on, I just gotta pull up the window. It's gonna take me a second.
So this will be chapter 4, number 47.
I think like what makes this kind of complicated for me is that I've never, like, everything we've covered in this class is completely new to me. I've never taken a physics class, and the first thing that I resort to is kind of like algebra and filling in all of those letters and all that stuff. So that's like what my mind jumps to originally.
Sure. And this is a new way to think. And I'll tell you, you can learn a lot more about math in a physics or an astronomy course than you ever could in a math class, because math by itself just isn't very fun. But it is fun when there's meaning behind what you're doing, and you can think about cool shit like, I like space. I like to think about stars and planets. That's interesting to me. So this is a good place to learn the math. You just have to accept that you're going to be stumbling forward, okay? So just let it happen. Okay, Sabrina, do you have that guy for me here?
It's loading. It's loading.
Oh, I see.
Just waiting.
Well, your computer's or your internet is slow, huh?
Yeah, it's still loading.
Okay, all right.
Let's like this.
Let it load. Can someone else read that for me? Mateus, how about you?
I have it. All right. So 47, head to foot tides. You and Earth attract each other gravitationally, so you should also be subject to a tidal force resulting from the difference between the gravitational attraction felt by your feet and that felt by your head, at least when you are standing. Explain why you can't feel this tidal force.
So let's translate what he just said into a picture. I want you guys to draw a diagram with me. First, we're going to draw the Earth. Next, I want us to draw the radius of Earth. I'm going to draw it in vertically this time. And to put a sense of scale on this thing, the radius of Earth is 6,400 kilometers. Let us now put a man standing on Earth, or a woman, whatever you like. Do you guys know the average height of a man in meters? How many meters tall is a typical man?
1.7 meters.
True, I agree with 1.7, but why don't we round that to 2, just for loosey-goosey fun, okay? I don't want to be schlepping around 0.7s in this exercise. Sometimes people will approximate 2 meters as roughly the height of a man. What this question is saying is 2 meters is a non-zero length. You have some dimension to you. And therefore, your feet are a wee bit closer to Earth's center than your head. Therefore, if you imagine chopping yourself into little cheese grater bits, there should be a force of gravity acting on your feet. Let's call that force F sub foot. And there should also be a slightly different force of gravity acting on your head. Let's call this F sub head. Now, I just want to make sure this is as obvious to you as it is to me. Which of these forces, in theory, should be greater? F sub foot or F sub head?
F sub foot.
Yeah, because it's a wee bit closer to Earth. By the way, when you are attracted to a sphere, the sphere underneath your feet acts as if all of the mass is concentrated at the very center. Okay. Therefore, there should be a tidal force. What do you guys think the answer is? Why doesn't a typical person notice the tidal force that's acting on them every day?
Gravity?
Well, the answer's got to be more complicated. I mean, gravity is the origin of both of these forces. But the tidal force is not gravity. The tidal force is the difference between these two forces. I'm almost tempted to make you guys calculate it as punishment.
Is it because the distance is not long enough to be felt? Like it needs a bigger distance for you to feel the discrepancy between
What's it? What distance are you talking about? Because we've got two here.
the 2 meters. The height of a person is too little to be for you to feel the difference from your feet to your head.
That's essentially the correct answer. If you want to make your answer even better, Mateus, you would say the 2-meter height of a man is such a small percentage of the radius of Earth that the force that your feet feel and the force that your head feel are so nearly identical that you don't even notice a difference. And yes, as you said, if a man was taller, if you had a height, you'd have to be even taller than the Empire State Building. You'd have to be even taller than Mount Everest. If your height was like 1,000 kilometers, then maybe you would start to notice it. But okay. Literally 2 meters is millions of times smaller than 6,400 kilometers, right? Remember that if a kilometer is 3 zeros, in meters, the radius of Earth, if you add 3 more zeros, is 6.4 million meters. So literally the height of a man is millions of times smaller than this distance here to the center of Earth, right? Okay, so let's write that down. A person will not feel a tidal force acting across their body because the 2-meter height of a person is millions of times smaller than the radius of Earth. And I'm not done yet because I want to talk about that tidal force to make sure that you all understand it. Therefore, the difference in force, and that's the key concept, therefore, the difference in force between Earth's gravity on your feet and Earth's gravity on your head, the difference in force is essentially almost zero. It's not quite zero, but it's so tiny that it might as well be zero. It's not enough for you to feel it. And yet, in a strange sense, it is there. That's how we do this. Notice this has nothing to do with the moon. You can feel a tidal force from Earth, just like Earth can feel it from the moon. By the way, Later on in this class, we will discover there are weird objects like neutron stars that can pack a tremendous amount of matter into a ball the size of Boston. If you were to stand on a neutron star, your 2-meter height would be a much greater fraction of the 10-kilometer radius of a neutron star. And in that case, you probably would feel tidal forces that would yank your body apart. So there are places you can go in this great galaxy where tidal forces could be felt even by a single person. Andrew, friends, let me know when you're done here so I can erase and move on. That takes
I'm all set.
Okay. Number 47's down. I'm going to erase. Here I go. Okay, Mia, why don't you dial up a little bit of 56 for me?
Okay. Gotta find it. Give me a second. Okay. Understanding Newton's versions of Kepler's third law. Find the orbital period of the planet in each case. Hint, the calculations for this problem are so simple that you will not need a calculator.
That's false, obviously, right? That's not true. Newton's version of Kepler's third law.
Part A.
Yep.
A planet with twice Earth's mass orbiting at a distance of 1 AU from a star with the same mass as the sun.
All right, let's start by writing down NK3, which is what this problem is about. So go ahead and write that formula down. P squared equals 4 pi squared times A cubed over G over the sum of the masses. In part A, our job is to find the period. Now, can you help me there? The mass is the same as the sun, right? But did you say, Mia, twice the mass of Earth?
Yes.
So one mass will just be the mass of the sun. The other will be twice. Oh, by the way, I'm going to start using some symbols, and I probably should introduce them now. From now on, a circle with a cross in it is the astrological symbol for Earth. And the astrological symbol for sun is a circle with a dot in it, okay? So I'm going to start using these all the time. Might as well introduce them now. This means sun, and this means Earth. Note to self. And Mia, what did we say the distance was?
Of 1 AU from a star with the same mass as the sun.
Okay, let's look at our notes from today's class, and let's do a quick memory jog on what all the units are that we need here. What units does the period appear in? You can look at your notes and just read off the notes. I told you what units P must be in.
Years.
No.
Was it seconds?
Yes, this is MKS now. By the way, the distance is not D here, the distance is A. Sorry about that. All right, P needs to be in seconds. What units does A need to be in?
Meters.
Meters. And how about the masses?
Kilograms.
Good. So we're going to have to deal with that before we get started here, okay? Let's just do the easy thing first. Let's convert A into meters. 1 AU is 150 million kilometers. What do I do to convert that into meters? Amy? Amy, my friend, why don't you help me do
Yeah.
that? I want to convert
Do you
that.
want to do the division bar?
Yes, I do. Okay. Now what?
Put meters on the top and then kilometers in the bottom.
Correct. Do you know the conversion?
Yeah, it's 1,001 in the bottom.
Good. Can you add 6 plus 3?
That's 9.
So what should I write?
150 times 10 to the 9th meters.
All right. So that's our A. Check. That's good. We'll be able to plug that into our equation. Because this is like an addition of masses, we're now going to analyze the addition of masses as a separate issue. I sometimes refer to the total mass of the system as the sum of the two masses. And in this case, the total mass is the mass of the sun plus twice the mass of Earth. And what I'd like to do is I'd like to substitute in the values that I gave you in today's lecture. The mass of the sun is 2 times 10 to the 30 kilograms plus 2 times the mass of the Earth, 6 times 10 to the 24 kilograms. Take out your calculators, add that up, and tell me what I get. 2 EXP30 plus 2 times 6 EXP24. Go ahead and punch it in.
I got an answer. I don't know if it's right though. I might have missed
Okay,
this stuff.
let's hear it. Let's find out.
But I got 4.54. Well, the 54 is the EXP.
All right, wait. That's not 4.54. That's 4 times 10 to the 54.
Yeah, I said that wrong. My bad.
Kiana, that's not correct. I think you did not hit plus there. Can you try it again, hitting plus this time?
Yeah, I got you.
Because look at this. If you did times, then you'd get 30 plus 24 is 54. So you hit times, but you should have hit plus.
Yeah, I did.
All right, try that again.
Yeah, I got something completely different this time.
What'd you get this time?
This time I got 2.000002 and then
Okay,
to
whoa,
the
whoa. Why
power
are
of
you
30.
playing me like that? Kiana, don't we usually round tastefully here?
Yes, we do. We do
All right,
round.
could you round that tastefully for me?
So would it just be 2.0?
Okay.
Then to, how did you say it? To 30?
Times 10 to the 30 kilograms.
Yes.
If you want 2.0, fine. I'm just going to say 2 times 10 to the 30 kilograms, okay?
Oh, I didn't know I didn't have to add the 0.
It's the same. I mean, it doesn't matter. The only thing that's weird about that, Kiana, is 2 times 10 to the 30 is the mass of the sun. Weren't you supposed to add the mass of twice Earth to that?
Yeah.
So how did that work? How can you get like mass of sun plus the mass of twice Earth is the mass of the sun? That's kind of weird, right?
Yeah, that is. Now I'm confused.
Now I'm confused. I don't know what to make of this. There's
So
something
this-
going on here, Kiana. We got to get to the bottom of this. Did anyone else get that?
I got it.
the answer.
Well, why?
Would it be 4? I'm taking a.
Nope. That is the correct answer.
Oh.
I just want to understand how that happened. How did I add the mass of a star plus the mass of a planet twice that of Earth and end up getting the same mass as the star?
Maybe somehow the mass gets negated, so that's why it ends up equaling the same thing.
In fact, as a matter of fact, Kiana, you're right. Adding the mass of the sun, which is a 2 followed by 30 zeros, to the mass of a planet, which is a 12 followed by 24 zeros. Okay, the mass of a planet is certainly greater than your pet chihuahua or something, but compared to the mass of the sun, the planet's mass is like negligible. Literally, this number has 6 more zeros than that number. And if you add $1 to $1 million, do you want to know how much money you have? $1 million.
Pretty much, right?
Because the $1 doesn't matter. And that's exactly what happened here. And this is an important trick that you need to know about. Sometimes we can neglect one of the masses. You have to be able to know when to do this. But you can neglect the mass of the planet because it's small. And thus, the sum of the masses will simply become the mass of the sun. And that makes the problem a whole lot easier. Okay, we have our A, we have our M, we know big G, we know 4, we know pi. It's time to calculate P. Are we ready to go? I'm going to need some board space here, so I'm going to need to erase this. Still part A. I want to start by writing my answer symbolically. I'm going to take the square, move it to the other side to get a square root. The period is the square root of 4 times pi squared times a cubed over g times the mass of the sun. That's what we're going to do here. And now we're going to put in some numbers. The period is, make a nice big neat square root. We have to put a lot into this here. 4 times pi squared times, I'm going to use parentheses here, 150 billion meters cubed divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared. Times the mass of the sun, 2 times 10 to the 30 kilograms. And now, this is where the suck begins, okay? Teaching you guys how to plug this in is going to suck a little while for me, so I'm going to have to just gin up and bear it. Y'all going to be making mad mistakes, and I'm going to be picking up the pieces of your crappy calculator skills. And we're going to deal with that right now. First, make sure you have this written down, and then we got to have a little sesh, okay? All right, I'm going to assume that you have everything written down. Before you even punch, let's just strategize. I need you to because you're about to get lost in the pushing the buttons and you're going to be all confused. You need to understand what's happening here. We're going to do the square root at the end, okay? We're going to do this times that squared. We aren't going to use any parentheses. We're going to do times 150 billion. We're going to cube it. And here's the important part that no one ever listens to me about. We're going to divide by big G, 70xp minus 11. And even though it says times right there, you with me, Tegan? I'm calling you up, Tegan.
Hi, sorry. What was the question?
Tegan, I need you to listen to this part real careful, because if you don't listen to this part, I'm going to have to help you every single day until the end of the semester. This part is a kind of really important. When we get to the bottom, you're going to hit divide, even though it says times, okay? We're going to divide by that number, and then we're going to divide by that number. We're going to hit equals, and then we're going to square root it. You guys do this? All right. I need your sharpest focus and attention right now, because it's always hard. James Sowers, what's your question?
In the red at the very bottom behind you. Yeah, what is the M3 divided by kilogram times, what is that?
Seconds squared.
Oh, okay.
So the way we say it is meters cubed per kilogram per second squared.
Okay.
Sorry, the red is a little hard to see. I might want to use blue for units from now on. Okay. James, do you have all that written down now?
Yeah.
I don't want to start. James, do you have your bloody Casio? You better have your Casio.
I actually have a TI-84, but I'm doing fine.
Oh, man, you are pissing me off left, right, and center. James, buddy James, who wants to come back into my class because he didn't do any fucking work for the first 2 weeks. I'm considering letting you back in, but there's no fucking way you're getting back into this class until you have a Casio FX260 Solar, because you, our son, are going to straighten up your act, and you are no longer going to be a pain in my ass. Getting this calculator is the first step to you not being a pain in my ass. Right now, you're a pain in my ass. All right. All right. So I don't care. I don't care how hard your life is, James. This cost $8 at Walmart. You will go today, you will buy it, and you will be happy. In fact, I think I'm going to make a requirement for me giving you the override. You're going to send me a picture of this. That's the price of admission. $8 is what it costs to get back in this class. And if we can talk about this at the end of office hours today, if you want to strategize with me.
I'm glad I can get it at Walmart. No.
Well, wherever you got to go, you go there and you get it by hook or by crook. Now, James and other people who are unorthodox and can't follow simple instructions, you're going to have to put in the square root first. I don't want to deal with your TI-84. If you know how to do it, then great. The rest of you, watch closely and punch along with me. Let me get my autofocus up and ready here. Okay, so that should be pretty good. All right, so let's begin. 4 times pi squared times 150 exp9. Now we got to do the cube. Ready? Shift cube divided by 7 exp negative 11 divided by, remember that, divided by 2 exp 30. Now we equals, and now we square root. Shift square root. This is what you should have. Let's see who did it right. Hold on, let me go to, all right. Yes, Amy. Yes, Tegan. Yes, Mia. Kiana?
I didn't get it.
All right, we're going to have to deal with it. This is why the suck happens. Tegan, did you get it? Yes, Andrew. I like it. Tegan? Tegan's not even with me. Nick, can you show that to me? You just dropped it. Nope. Sorry, Nick. No good. Okay, so we got...
my calculator wouldn't turn on in the beginning, so I had to do it myself the first time and try to follow along.
And that doesn't work, yeah. So we got some Nick issues. We got some Kiana issues. Hey, James, did you get it with your fancy TI-85?
Oh,
You didn't, did you?
no, I did not.
Exactly. That's why you're not allowed to use that calculator. All right, Tegan. Hey, Tegan. You need to practice this, Tegan, my friend, because this is going to suck really bad come test time if you can't do this. Do you have your calculator?
Yeah, I do have my calculator. I punched it in. Wait.
Okay,
Square
Mia,
root.
I'm sorry about that. Get the rest of it later, okay, buddy?
Sorry about it. I got it on the calculator, so we're good.
All right, that's something.
Bye.
Okay, we got to do this again. So the problem, Nick, the problem, James Sauer, that I explained a million times before, is when everyone has a different calculator and sucks at math, then this becomes impossible. So what I need is it's okay if you suck at math, I just need you all to have the same calculator. For you, buddy, you should use the square root first and open parentheses. But besides that, you should be doing everything that we're doing. And you probably don't even know where your fucking EXP key is, but I got a Casio TI-85. I know how these things work. Every time I say EXP, you should be using your double E key. That's your EXP. And you should be using your squares and cubes just like I do. All right, let's try this again because it's not worth it unless everyone can get it. We're going to do this one more time. I'm going to go slow, but stay with me here. 4 times pi squared times 150 EXP 9 shift x cubed divided by 7 EXP negative 11 divided by 2 EXP 30 equals shift square root.
I missed the square root the first time.
Okay. Yes, Tegan, you make me proud. Sabrina, it's a little dark. I can't see. Did you get it? Do you have what I have, Sabrina? Oh, bloody hell. Oh.
No, it came up to 2 point something. I don't know. 2.3. I don't know what the heck I did.
No, it's not about, it's about this. Can I see your number? If I can see your number, I can tell what you did.
It keeps dying.
Oh my God, I don't know what you did. Times 10
Me either.
11. All right, okay, I don't know what you did. One more time for the people in the back. Okay, here we go.
Okay.
Clear it out good.
Clear it out. Oh,
Are you with me, Sabrina?
the light. It's the lighting, but
some
it's
light.
fine now. It's the light's coming down on it.
4
4
times
Yep.
pi squared times 150 EXP 9 shift x cube right there.
Yep.
Divide by 7 EXP negative 11
Yep.
divide by 2 EXP 30 equals
Yep. Got the same.
shift
Oh, sorry.
square root.
Shift square root. Yeah.
Thank God.
Good.
Okay.
I finally got
What?
it. I see what I was
Oh my
doing wrong.
God.
You guys will get
That's
you guys will get better at this. It's just gonna suck for a little while, but we're gonna get better.
It does suck.
All right.
Yes.
No, wait, the suck isn't done yet. Now we have to interpret this.
Oh,
How
oh
should
well,
I write
it's
my
not
answer?
too bad.
First of all, we have a rule in this class. Is this number bigger than 1 million? Yes or no?
1, 2,
It
3,
is.
4.
That means we got to do scientific notation and we've got to do rounding, and we need units. Who can
Yep.
figure out what I should write down?
I think you should write down. So the significant number, can we have two significant numbers?
I think
Yes
two
or no?
significant figures is great.
I would say 31.
Okay, 31
Um,
times 10.
to the seventh power or sixth power?
Okay, hold on. If you're
Not
going to do
power.
31, then you're moving it 6 times. If you're
Yeah.
going to move it 7 times, it's 3.1. You started off by saying 31, so I was going with you. 31 to 6. Fine.
Okay. Yeah, because of the second digit. Okay.
You could also write this equivalently as 3.1 times 10 to the 7. I thought you were going to do this. You did that. I'm okay with it.
Okay.
But make sure you know how many times you're moving your decimal place. This is the same thing. What are my units?
It's
a period.
Is it kilogram? It's kilograms, right? Oh no.
Period is a time. You have to give units of time. Mks units of time. Shout it out if you know anyone. Seconds.
Seconds.
Exactly. And that's correct. 31 million seconds.
So I want to make sure I have this right. In the beginning, when you said we have to divide by the 2 times 10 to the 30th instead of multiplying, is it because that that G equation isn't really part of the problem? It's just the formula. So
No.
really,
it's Nick. I'm glad you brought this up because this is an issue.
you know what I'm trying to say?
I do, but I need you to think about it differently. Nick, suppose I asked you to do this problem in your head. 6 over 3 times 2.
Is that 1?
That's what it should be. But watch what happens if you plug it into your calculator like that. Watch. If I go 6 divided by 3 times 2, I get 4. And the reason why I got 4 is because of an order of operations issue. The calculator first did 6 divided by 3 and it got 2 in its brain. And then once you hit times 2, it thinks you want the times 2 to be on top. So it does 2 times 2 is 4. You have to hit divide because the calculator doesn't know that you want that to be on the bottom unless you tell it to be on the bottom. And the only way to tell it to be on the bottom is to hit divide again. So the calculator knows this is on the bottom, but this is on the bottom too.
Okay.
I think didn't you say something about that last week too?
I did, but it turns out that saying things once is never enough.
Yeah,
You have to
it's
say it
not.
like
Yeah.
Absolutely right. Because I don't remember. I remember, but I don't remember. I get it.
This is part of the nature of education. Folks, one does not learn a thing by hearing it the first time. You learn it by hearing it like 5 or 6 times. So we have to do that. We have to go through this awful process. Okay.
Sounds good.
We're not done here. There's a point to this problem, and I need you to see the point, and we have to move on to the other parts. We're now going to convert this to years. And because I'm concerned about time, I'm going to give you the conversion. I'm now going to give you a very important conversion that will be helpful in this class. Write it down on the side of your paper. 1 year is equal to 3.15 times 10 to the 7 seconds. The way astronomers memorize this conversion, because we need this all the time, 3.15 is wicked close to pi. So astronomers remember the number of seconds in a year by joking that 1 year is pi times 10 to the 7 seconds. Not really true, but it's close enough to the truth. So that's a mnemonic to help you remember it. Pi times 10 to the 7, all right? Now, let's do dimensional analysis and let's convert from our answer into years. 31 million seconds times seconds on the bottom, years on top. 1 year is 3.15 times 10 to the 7 seconds. And what do you get? Shout it out, folks. We ain't got all day here.
0.98.
Or approximately wicked freaking close to 1 year. And what's so very sad about this problem, the hideous trick that I played on you, is all of that work could have been avoided if you stopped and thought about it. A planet orbiting the sun at 1 AU with a mass equal to that of the sun will have the same period as Earth, 1 AU. That's because the mass of the planet is not significant enough to affect the orbit around the star.
Is that like kind of the same thing where we don't feel the effect of it neither on Earth? Or like what is no, is this something totally different? Maybe the head to toe thing?
It's different, but these sorts of games are played. This is an important part of learning to think like a scientist, is sometimes you can intuitively understand the answer by it is similar in a way. We don't feel tidal forces because our size is too pitifully small compared to the size of Earth.
Mhm.
In this case, the orbital period of a planet usually only depends upon its distance and the mass of the star, because normally the star is way more massive than the planet. Let's try part B of this problem. Yes, there is a part B. There'll be another chance for you guys to work on your chops with your calculator, and we'll see it's not the same in part B. So I'm going to erase here. These problems will go faster as you guys get stronger, but right now you're very, very weak, and we need to build up your muscles. Okay. All right, let's go to it. I don't even remember who the reader was anymore. I think it was Mia. So I don't know. Who's got the problems handy there?
I can read it.
Yeah, could you do that, part B?
Yeah. What number was it again? I haven't pulled up here.
56.
56. All right. Scrolling down here.
Oh.
All right, so we're on B. All right. A planet with Earth's mass orbiting at a distance of 1 AU from a star with 4 times the sun's mass.
Okay. Remember in our last problem, I think it was Kiana or Mia, or Amy, sorry. Amy helped me work out 1 AU into meters. So we already have that going. I want you guys to notice that this problem is different. It's different because the mass is the mass of Earth, but the star's mass is 4 times the mass of the sun. Therefore, the total mass of the system is 4 times the mass of the sun plus 1 times the mass of Earth. Do you guys see any simplifying assumptions that we can make here? I need to get a number for all this stuff. Okay, fine. If you don't understand me, then we're going to have to plug it all in. 4 times the mass of the sun is 2 times 10 to the 30 kilograms plus 6 times 10 to the 24 kilograms. If you don't understand what I did last time, you're going to have to keep doing it until you do understand. And I want you guys to punch that in and get me an answer.
Come on.
I got something, but
Tell me
Yeah,
what
I
it is.
have something.
Give me your somethings.
8.
That's what I got.
yeah, I got 8.0006.
I don't care about the points. The points bore me. I want to know the
I just wanted to tell you.
So
Okay.
it's 8. So when you round it, it's gonna be 8 and equal exp 30
8 times 10 to 30 kilograms.
Yeah.
In other words, it's 4 times the mass of the star. What I was hoping somebody would see, but nobody did see,
Are you okay?
is that the mass of the planet is tiny in comparison to 4 times the mass of the star. You guys still hadn't learned that lesson, so we had to plunge it all in. Whatever. We've got 4 times the mass of the sun right there. Now, let's set up our equation. Just like last time, P is going to be the square root of, this time I'll do units in blue because James was having trouble reading the units. 4 times pi squared times 150 billion meters cubed divided by big G, which is always 7 times 10 to the negative 11. The units are meters cubed per kilogram per second squared times 8 times 10 to the 30 kilograms. Oops. That's 4 times the mass of the sun. Wow. Okay, let's see if you can remember what we did. Your job is to get me the answer without me showing you what to do. Let's see if you can do it. Punch them up.
Anne Marie, turn off the TV, please.
And while I'll wait for you to punch them up, I'm gonna listen to this cool jam.
I got an answer.
Okay, cool. What'd you
So
get?
I got 1.5 times 10 to the 7th seconds.
Crushed it. Crushed it. Love it. 1.5 times 10 to the 7 seconds is exactly what I wanted to hear. How many people struggled with that? I'm sure a few of you did.
Right, yeah. I'm
All
one.
right. All right.
The calculate. I'm not good with the calculator yet. I'm not like.
I know you will be, Sabrina. That's why we're doing this. This is
Yeah, that's what's killing me right now.
Can you say that one more time? I'm not sure if I oh nope, did not get that. I think I'm hitting equal before I hit square root. I'm just hitting square.
That's
I
what-
just need to hit square root.
Wait, who's talking to me right now? Nick?
It's Nick, yeah.
Yeah, you have to hit equals before you square root. That's important.
Yeah.
But there's about 10 million places you can screw this up. And you guys are going to screw up all 10 million of them before we start getting it right. I just know this because I do this every year or every semester. Okay, if you tried and you failed, that's okay. Let's just do it together. Let me get the zoom in here. Okay. I'll try to go slow, but I don't want to go too slow. Clear out your calci. 4 times pi squared times 150 exp9 shift cube divided by 7 exp negative 11 divided by 8 exp 30, then equals, then shift square root. Notice Andrew quickly put this into scientific notation as 1.5 times 10 to the 1, 2, 3, 4, 5, 6, 7. Sabrina, did that work a little better?
Yeah.
Be honest.
Yeah, but to be honest, I keep getting confused with like when, you know how we have the parentheses, like where what key to take to
Right.
put things into
In other
parentheses?
words, Sabrina, you're saying, why are you playing me with these parentheses if we're not going to actually put them in the calculator, right?
Yeah, that's what's kind of confusing me.
So I tried to explain this earlier, but I don't think your ears were ready to hear it yet.
Probably not.
The reason the parentheses are there actually have nothing to do with the calculator.
Okay.
It's about units. You see, although it won't seem like a big deal to you, I know that if I do not put those parentheses there, there will be an ambiguity about whether or not the cube should go to the meters or the cube should go to the number. The
Okay.
parentheses tell the reader the cube goes to both. But you don't plug units into your calculator, just numbers. And since you have an EXP key, the cube will apply to the whole thing. Look, you just got to trust me. Let me just say it simpler, okay? Here's what really matters. You write the parentheses, but you don't punch them in. That's all there is to it.
We don't. Okay.
You write them, but you don't punch them.
Okay.
Let's just say that to start.
I'm sure there'll be more examples.
Oh, there sure will, Sabrina. This ain't the last thing. In fact, the next problem is going to be more examples. So you're going to get good at this pretty quick.
Okay.
Okay.
Let me get ready.
How many, hold on a second. We now have to convert this to years. I want to know, class, and I'd like you to be able to do it with less training wheels. How many years is this? Convert it to years using your conversion factor and your powers of scientific notation. At some point, I need you guys to be able to do dimensional analysis. Sorry, dimensional analysis, not scientific notation. I need you guys to be able to do dimensional analysis without my help. Let me go up here. Erase. In other words, I want you to do 1.5 times 10 to the 7 seconds. I want you to convert seconds into years with that conversion factor.
It's not going to be 2.1, no?
Nope. This number is smaller than that number. You're going to get a number less than 1.
Okay.
There's a times, but this is on the bottom. So really what I'm asking you to do is to divide those two numbers.
Because I just went ahead and I tried to convert it by using the conversion factor of 3.15 that you gave us.
Right.
Dividing it, but I think I maybe did it wrong.
Well, that's right. That's what you should have done. So
maybe I did it backwards. Yeah.
Hey, Zach Plant in the background. Why don't you round that even harder for me, buddy? Round it real hard. Yeah. Zach's point is this is half a year. Okay. Now, I'm going to open up a can of mathematical whoop-ass on y'all. And I'm going to show you that if you had been able to wield the power of proportionality arguments, you could have solved this problem without any of that craziness. And here's how the book thought you might do it, but you weren't ready for this yet. But well, first of all, can I erase this? I need some space here. All right. Let me show you another way you could have solved this problem, because I want to show you how proportionality symbols are powerful. I know that the Newton's version of Kepler's third law looks like this, where I've replaced m1 plus m2 with the total mass. But I noticed that 4 and pi and g are just constants and they never change. So I could write this in a proportionality argument as p squared is proportional to a cubed over the total mass. Remember, in this problem, we had a planet orbiting at the same distance, but with 4 times the mass of the sun. So using proportionality arguments, the distance stays the same, but the mass varies by a factor of 4. If p squared is proportional to 1/4, because after all, 1 cubed is just 1, then taking the square root of both sides P is proportional to the square root of 1/4, which is half. The meaning is the new period is half of the old period. So if you had been able to wield a proportionality symbol, you could have solved the same answer without plugging in any numbers and doing it all in your head. But y'all ain't ready for that, because this, my friends, is blue cheese. And you have not yet learned to appreciate the tangy tartness that is the proportionality symbol, okay? It's something that's subtle. You have to learn to apply it. I wanted to show you that it can be used to great effect. You guys are still at the stage where you can't even punch things in your calculator, so you got to do it the hard way. You have to suffer a little bit. Okay, let's move on. We got more to do here. I'm going to try to speed things up, but I can only go as fast as you guys can handle it, okay? Today's homework is a little bit of a learning curve. It's going to be a little bit of a stress case, all right? I'm erasing. We're getting to it. All right. Hey, Sabrina, did that thing ever load for you? You want to do some reading for us? I'll get around to that later. Sabrina, can you read 57?
Okay, let me see. Using Norton's version of Kepler's third law. Part A, calculate Earth's approximate mass from the fact that the moon orbits Earth 27.3 days at an average distance of 384,000 kilometers.
Okay. So let me explain what's going to happen here. In our previous problem, we used NK3 to find the period of a couple of different planets. Let's start by writing down MK3. In this exercise, we're going to use this equation for a different purpose. Instead of solving for the period, they're going to say, what if we know the period and we know the distance of the planet? Can we then solve for the masses? To do that, we have to rearrange this equation. M1 plus M2, so I'm going to flip them up top, is equal to 4 pi squared a cubed over g, and I have to flip the p squared down, times p squared. I want you to write that equation down, and I want you to put a box around it. This is also Newton's version of Kepler's third law. But it's Newton's version of Kepler's third law solved for mass. And it is a very important formula in astronomy. To be honest, kids, the reason I taught you this was because I wanted to teach you this. This is the point. This is what we've been getting towards, but I'll explain that later. For now, let's just see if we can do some plugging and chugging. We need to convert our units. In part A, Sabrina says that we have a period of 27.3 days, and we have an orbital distance of 384,000 kilometers. We're going to use the period of the moon and the distance to the moon to calculate the mass of Earth. Now we got to think about our units. Days and kilometers will not do for this equation. Nick, what units do I want?
I'm gonna have to look back at the question.
You can look in your notes today where I introduced this equation and I told you what the units should be for each
It
letter.
was meters. Talk about the MK system.
Yes, I am.
So it'd be meters, kilometers, and seconds, or kilograms. I'm sorry.
Meters, kilograms a second. So this will have to go to seconds and that will have to go to meters. Why don't you do this conversion and I'll make someone else do the second one. So Nick, 27.3 days. Help me convert to seconds.
3 days. So it's going to be the division bar.
Correct.
You're going to do days on the bottom.
Yep.
And you're solving for.
We're
I
solving
forget
for
the-
seconds, but you probably don't know the number of seconds in a day unless you're memorize the Rent song. So what do you want to
No.
convert days into? Let's convert it into another unit.
Seconds? No, not seconds.
The question is, what can you convert days into that's closer to seconds than days?
Years? No, that's further from days. Nope, I'm
Right.
sorry.
Further from seconds, you mean?
Hours.
Hours.
That's right. Okay. That'll take care of days to hours. Then we have to keep going. What's our next conversion?
Hours to minutes.
Good. And then?
Minutes to seconds.
All right, hit me with the conversions.
All right, so it'd be 24 hours, 1 day, 60 minutes, 1 hour, 60 seconds, 1 minute.
Nicely done. Okay, let's punch them up and give me an answer.
Two times 10 to the 6 seconds.
Let's do 2 sig figs on that.
23 times 10.
Just make it 2.3.
Oh, 2.3 times 10 to
Wait,
the
what's the
6.
number after 3?
5, so 2.4. I'm sorry.
That's all right. 2.4. Keep going.
Times 10 to the 6.
Okay, cool. Yeah, a thing about that, Mateus and friends. These are numbers that are going to go into another calculation. Keeping 2 around because we're going to be plugging stuff in will help with some errors. So sometimes at the end we round back, but you want to keep at least 2 when you're plugging stuff in there, okay? Honestly, you probably could have rounded it and still got close to the right answer, but okay. Mateus, just to make sure that you've got your chops intact and for the interest of time, why don't you help me do the 300? Actually, you know what? No, Mateus, you've seen too much of this. Sabrina, I want to work on your chops, okay? Come on, Sabrina, help me convert this from kilometers into meters. I know you can do it.
All right, so you want to do the division bar.
Yep.
You're gonna put the kilometers at the bottom, meters at the top.
Yep. And now we need to know meters to kilometers.
Okay, multiplied by.
No.
No?
Your units are good. We want to get to meters, right?
Yeah.
So what I want the numbers now. That's
Okay. So 1 meter, right? Is it 1 meter to 300? Oh no.
Nope, that's not the conversion. The question is how many meters are in a kilometer? If you look at some of the previous problems, you might see the conversion. For instance, in the last problem, we had to do this. Amy helped me with it. But why don't you hunt around, Sabrina, see if you can find that yourself.
I think I have it.
Okay, sure.
You said a kilometer to or kilometer to meters, right?
Yep.
It's 1,000 meters
Yep. Is how many kilometers?
is 1.
Exactly. So Sabrina, if you look around your paper, soon enough, you'll see that we have that conversion several places.
I see it now.
Okay.
Number 56, actually.
Right. So does anyone know, how should I write this out then? We don't need a calculator, just put the zeros into a power of 10. What should I write?
Right.
Do you know, Tegan?
Is it 384 times 10 to the 6th?
Beautiful. That's just what I wanted to hear. And that's meters, right?
Yes.
Okay. all of that, guys, that was just getting our units in the right place. Okay, you'll get faster at this eventually, but right now, every single thing you do is like a big adventure. So now you got your units in place. Now we're going to plug it in, but I'm going to have to do some erasing. Get all that down. Is anyone still working, or can I erase?
I'm good.
Here we go. Okay. Remember that NK3 for mass tells us it's the sum of the masses. Since we're dealing with Earth and the moon, it's the mass of Earth plus the mass of the moon is going to be equal to all that crazy stuff. 4 times pi squared times, open parentheses just for fun, Sabrina, 384 times 10 to the 6 meters cubed divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times, parentheses just for fun, 2.4 million seconds squared. Okay, let's see if anyone can get the answer without my help. Just try it on your own. Yes, Mateus, you got it. Why don't the rest of you punch up too and see what you can do? And then we'll do it together if it doesn't work so well. Let me keep an eye on the chat. I know some of you people in the shadows there are either camera shy, audio shy, or don't have cameras and audio. That's possible too. So Mateus, you got it, but let's give these guys a second or two to bash around here. It's good for them. That's the whole purpose of this live thing. Tegan, I'm trying to see what you got there, buddy. But there's glare and can you hold it back a little bit? Oh. You are close, but you're off by approximately a factor of pi. So I think what you did, Tegan, is you forgot to square your pi. That's the only thing you did wrong. Nick, you got it correct. Nicely done. Nice. You guys are getting this now. Tegan's going to give it another whack. How about the rest of you cats? Let's see here. Amy, you got it. Nicely done. Okay, I'm starting to feel good here. I'd like to get a few more of you guys hitting this. Andrew, tell me what you get. So far we got Mateus, Nick, and Amy have got it. Tegan's almost got it. I don't know how my trolls are doing here, but. Bang, Tegan's got it. Andrew, and Sabrina, it's just you guys here.
I got this.
Okay, so I'm getting a bit confused. I'm on the very last part for the 10 EXP6, and then there's 2, and I don't know what to do. And I got so close that I don't want to mess it up.
10 EXP6. Oh, then you have to square it. Sorry, Andy, you're not quite there.
Yes.
Then you square it, and then you hit equals. Dying.
So I'm at the bottom also, right? And then I did the 7 times ESP 11.
Negative 11.
Yeah, negative 11. I think I did negative 11.
Yep. And
I think I did it right. I think I hit the negative 1, right?
no. What did you do after the 7 times 10 to the minus 11?
Nothing. What is the?
But
I'm
look,
just-
you gotta do that guy too, right?
Oh, so wait. Duh.
Divide, but here's the key.
Oh,
crucial
divide.
thing.
Oh, I didn't do that. I didn't
Divide by 2.4 exp6 squared equals.
6.
Oh, I think I multiplied.
Just for fun. Yeah, you can't do that. Ready? 4 times pi squared times 384 exp6 shift cube divided by 7 exp negative 11 divided by 2.4 exp6 squared equals. That was
Oh,
probably
that's
too
not
fast
good.
for you guys, but Sabrina, hold it up. What'd you get?
Oh, I'm way off. I don't want to show it.
Oh gosh. Yeah. All right, can we do it again slower then?
All right.
You want to do it with me?
All right.
Just-
Yeah. My
just
things.
Punch after me here. It's going to be like this for a little while until we all get on the same page. I'm sure people watching the video later will be appreciative of this too, okay? All right, here we go. Sabrina, are you good?
Yep.
All right.
I'm good. I'm waiting.
I think I got it. Did I get it?
Let me see, Andy. Hold on. Where are you? I lost you. Nope, Andy. You should clear it out and just follow along with me, okay? And the rest of you watch for your health, okay? All right, here we go. I want to keep an eye on Sabrina while I do this, because when I see your eyes go up, then I know you're ready for the next instruction. There you are. Okay. Here we go. 4 times pi oh, I think you're freezing. Squared times 384 exp6 shift cube.
Oh, that's why I went wrong.
Yep, can't forget that. Divided by 7
Divided by
exp
7
negative
exp
11. Here comes the big moment here. Divided by 2.4 exp6. We have to square that, bada boop, and then we hit equals. Yes, Kiana. What'd you get?
I think my problem is I keep multiplying 10, and that's why I'm messing up.
Yes, Andrew. Okay, so let me say that again, because Kiana, point taken, I knew that was going to be a big damn issue, okay? The single most likely place for y'all to screw up, the thing that screws people up the most, is they constantly forget that they have to put divide there. You'll remember me and Nick had a whole chat about this. The calculator needs to know that's on the bottom, so you got to hit divide. These are tricks of the trade that you learn by practicing, okay? All right, how shall we round our answer? Sabrina, what do you think?
I'm thinking 6. I'm gonna say 6.
Sure.
And
times 10
to the 24th power.
And
Wait.
what are the units?
Is it? It's not kilograms, is it?
It is, because that's
Is it
MKS units of mass.
Okay.
That's our answer. Okay, the only other part of this problem that we haven't addressed is this is the total mass of the system, mass of Earth plus mass of the moon. But they just wanted us to find the mass of Earth. Let's ask a veteran like Mateus. Mateus, what do we do about the mass of the moon part? I'm putting you on the spot, so I don't know if you know the answer, but we were supposed to find the mass of Earth.
Wait,
mass
I'm
of Earth.
kind of confused on the calculator thing. So is it shift x to the third and then divide?
Yes.
All right.
shift x to the third, then you go to the divide. Andrew, you got the right answer. I saw it on your calculator.
Yeah, but I'm just writing it down.
Oh, okay. Nobody? Do you guys understand the problem? What did they ask us to do? They said, find the mass of Earth. But this is equal to the mass of Earth plus the mass of the moon.
So you subtract the number that you found from that to find the mass of the moon? Well, you subtract that from, well, actually, no, I don't know. No.
It's a trick. The point is the mass of the moon doesn't fucking matter because the moon is way less massive than Earth. So even though this is the mass of Earth plus the mass of the moon, it's really just the mass of Earth because the moon is a small fraction of the mass of Earth.
Is
It's
it like that other
$1
problem we
100
did?
bucks. This is a trick that we constantly have to play and to know when can you ignore one of the masses. Okay, whatever. Jesus, oh, I'm dying here. That was part A. We are in double overtime right now. I knew today was going to suck. I just didn't expect it to suck this bad. Okay. Here's the strategy. This is what we're going to do. I am declaring martial law because this is taking us a long time. And for this week's homework, everyone, I'm letting you off the hook on number 58. You're just going to turn in 4 problems. I'm sure I'm going to regret that at a later date, but I just decided it because I would like to stop at some point. Okay. However, you do have multiple parts to this problem. That was part A. The least you can do in return is help me finish out this problem. Fair deal?
Yeah, that's fair.
Fair deal.
All right. I'm sure everyone's totally okay with that. So let it be known here and forevermore, probably no one who watches later will even make it this far in the video because they'll have stopped watching a long time ago. But for those sorry bastards, number 58 is Nick, right? Okay, Nick, can you read me part, wait. Nick, oh, I've got some very bad news. I don't even think we were supposed to do part A. We were supposed
Oh my God, no, we were supposed to do D, E, and F.
Mother
Oh
F.
my gosh.
All right.
Oh my God, I didn't say anything because I was looking at the wrong one. Oh God.
Okay, all right, let's now make another rule. Okay, we're gonna do E for a lab next class. That's how we're gonna do this. So instead, A, D, honestly, just A and D.
That makes an appointment to me.
A and D, okay? That's it.
People watching this later are going to be all types confused.
Well,
it's all right.
I know. The problem is, part of this is just COVID shit, because like when I'm working with you guys in person, I can zip around the room and do this a lot faster. It's really irritating to try to, but we have to do this. You understand, right? If we don't do this little calculator training process, you guys will never get good. This is unfortunately a difficult moment in the class where things get a little real for a minute. Okay, so I can help by cutting down the workload. So what we're gonna do is, in addition to not doing 58, because we already screwed up, and I'm gonna regret this someday later, A and D are the only ones we do. That way we'll do one more of these problems and then we'll just stop, for the love of God. Okay, so I'm gonna erase this now, okay? Let's see if we can crank out this last one a little quicker this time. Nick, read us part D.
Pull it up here. Part D, 57, part D. Calculate the combined mass of Pluto and its moon,
Charon,
from the fact that Charon orbits Pluto every 6.4 days with a semi-major axis of 19,700 kilometers.
Okay. I want to point out that unlike the last problem, where we could nix and neglect the mass of the moon, in the case of Pluto and its moon Charon, you guys have probably never even seen these guys before, but let me show you a sick high-res image from the New Horizons mission, Pluto and Charon. Pluto and Charon are different than the moon and Earth because, as you can see from this photograph, first of all, they look totally awesome. I want to just start by saying that. But the moon Charon is actually a pretty significant fraction of Pluto's mass. I think it turns out to be like Charon is roughly 1/3 the mass of Pluto. And because of that reason, this is the only place in the solar system where a planet or a quasi-planet and its moon are so close to each other in mass, some people consider them to be like a binary planet system. Because of this reason, we cannot neglect the mass of Charon. It's a significant fraction, but that's okay in this problem because if you do a close reading of what they asked for us to find the combined mass of Pluto and Charon. In other words, we're just solving for this. All we got to do is plug in our A and our P, and we got to get the right units. So tell me how to do that. How should I begin? Oh, okay, Kiana, do a quick break. That's fine. The rest of you guys, she can catch up. What should I do?
I would say convert those guys.
Convert them to what? That's correct. What?
So days, we're going to do days into seconds.
Okay, so let's do it quickly, just like we did before.
All right.
Andy, you seem to know what was going on, so we'll let you take the lead.
All right, so 6.4, so oh, wait, hold on. 6.4 days. So you're gonna times that by hour. Hour's gonna be up top, then day's gonna be at bottom, and then you're gonna times again, and then you're gonna have hour at the bottom and minute on top. And then you're gonna times again. Then you're gonna have minute at the bottom and seconds on top to get seconds.
Good. And I'll point out to the class, day cancel with day, hours cancel with hours, minutes cancel with minutes, only seconds remain. Okay, Andy, give me the conversion factors.
All right, so 1 day, 24 hours. And then 60 minutes, 1 hour. And then 1 minute, 60 seconds.
Punch him up. Punch him up.
$56,000 seconds.
Can someone else confirm that? Did anyone else get that? Don't make me do it, guys. This is a
No, I actually got
Yeah.
552,000 seconds.
Correct.
Okay,
That's what I got also.
Let's say 553,000. Okay. So there's a little whoopsie there at the end. Honestly, 3 sig figs is wicked overkill, but fuck it. All right. Okay, now I don't know. James. You still with me, James?
Yeah, I'm here.
Okay, why don't you earn your stripes here? 19,700 kilometers. Have you picked up enough in the short time that you've been with us to know how to convert that into meters? Do you know your 4 steps of dimensional analysis, in other words?
Yes.
Okay.
Okay.
Take me through it.
We're gonna start with the division bar.
Yep.
I mean, I guess I would put in 1 at the bottom, 1 kilometer, and 1,000 meters at the top.
That's not how we play, sir. Let me tell you, we have a method here, and the method is good because shit's going to get even more confusing than this, if you can believe it. Numbers are not allowed until your units are in place. That's my rule. So just
So
humor-
kilometers
humor.
on
Yep.
the bottom, meters on top.
Good. Now you can give me the numbers.
1 to 1,000.
Okay, 1,000 on top, right?
Yes.
Okay, and then what should my final answer be?
Should be in sec.
Yeah, how do we do this now? What's the best way to go? Don't punch it in, James. If you're punching it in, you're missing the point.
I am. Yeah.
You can do this in your head. Let me tell you how I would do it. I think in terms of thousands and millions and billions. I see 3 zeros there, and I see almost 3 zeros there. So I would go 19.7 times 10 to what power?
To the 5th.
Try again. There might be 5 zeros, but I moved to the decimal place between the 9 and the 7, right?
Right. To the third power?
Not to the third.
To the 6th.
Thank you. To the 6th, because I basically did a decimal point here, 1, 2, 3, 4, 5, 6, right? Whatever.
Okay.
Just take my word for it. Okay. Now we are ready to plug into the equation. Anyways, I want you guys to eventually get good at that. So I'm trying to show you how this works. The mass of Pluto.
I get that. I understand what you're doing though.
Good, good. That makes me very happy. All right, so 4 times pi squared. The A is 19.7 million meters, cube thereof, divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times, open parentheses, 553,000 seconds, close P squared equals. Okay. Punch them up, see if you can get it right. Let's put this day out of its misery.
Bless you.
Oh my God, what the hell?
Did something just happen, Sabrina? It sounded like a wall collapsed or something.
I don't know what just happened. I think the refrigerator just, the ice makers.
Amy, you've got it. Nick, can you show it to me again? Amy, you got it.
Oh God, I definitely don't think this is it, but
Nick, you got a little glare. Angle it down a teeny bit.
Yep, I'm trying to work on the glare here.
Just angle it forward, like in your pitch or your yaw, whatever that is.
I don't know
Right,
if it's gonna work. It's not bright enough in here.
stupid glare.
Nick, it looks like you got it. Andrew got it. Kiana, there's something wrong.
Yeah, I noticed something wrong when I was typing it in. I did something and then
Punch it again.
it
If you
disappeared.
get it wrong, just punch it again. Tegan, something's wrong.
Okay.
Sabrina's checking on the ice machine. Okay, look, we ain't got time for this jazz. Just watch me, okay? 4 times pi squared times 19.7 exp6 shift cube.
Oh.
Yep, divided by 7 exp minus 11 divided by 553000 square then equals. How should I round my final answer?
I see what I did wrong.
Good.
I almost got it. I just messed up on like 2 things, and that's what throws it off. But like I almost got it down packed.
You'll discover, Kiana, that as we continue to do this together, within a week or 2, you're going to be a lean, mean calculate machine. We just have a few speed bumps to hit until then. Okay.
I hope so.
So I promise you, it's going to get better. Meanwhile, I need an answer over here. I need it well-rounded, and I need units.
Oh, it'd be 1.41 or 1.4.
1.4 is good enough for me.
To the times 10 to the 22nd kilograms.
Excellent. It's ironic that the entire combined mass of Pluto and Charon is close to but slightly under the mass of our own moon. Anyways, okay. Wow. I knew today was going to be like this. It's a good thing I stopped drinking when I did last night. Okay. Or this day would have been even rougher. Okay, listen, all jokes aside, you did a great job. You learned a lot today. For people watching later, if you made it this far, the whole class can just turn in that as their homework assignment. Now, unfortunately, this last problem on escape velocity, we're going to have to deal with, but I'll include that as part of Tuesday's lecture, okay? On Tuesday, our lab will be on the period of the ISS. We're basically going to be practicing this even more. We need more practice. For now, what you did was sufficient. You can turn those in. Remember to turn them in from your computer, not your phone. That way I don't see it as a hyperlink. I think that's it. If James is still in the background, we can have a quick chat at the end about what I need from you to get you back into this class and for you to understand why I have conditions to come back into this class. Because as you can see, we move forward and we move fast. And anyone who's not watching the videos and keeping up with this is a drag on my psychic energy and my time. And I've got 168 humans to manage this semester, which is a lot of people. So I ain't got time for no BS, okay? So James, if you want to hang online for a minute here, we can talk after I stop the video. Does anyone else need or want anything from me or have any other questions?
I have a question.
Yeah, Kiana.
So speaking about the link, so sometimes I upload it from my computer and then sometimes I upload it from my iPad. Have you noticed a difference or is it good every time I upload it?
To be honest, Kiana, even though I know you because you interact with me and I love you to tears, what's really happening is I'm just scrolling through 1,000 people going, oh, motherfucker, there's another, like, you know what I mean? So I can't, because 168 people is so many to go through, I can't remember, but we could try right now. All right, Mateus, peace, buddy. Don't forget to turn that stuff in. Let's see real quick.
All right.
What did you do last time for the lab?
So the very last one, the one that I talked about, like way in the beginning of class for lab 3, that one I submitted on my iPad.
So let's see what happened. And Kiana, what's your last name again?
King.
King. Where are you? Huh. So why don't I see your submission here? Oh, what? No.
I sent it earlier. Did it not work?
Sometimes what happens is if you log out before you're finished, I'm starting to think uploading from the iPad's a bad idea. Let's go into my full grading section here. It's really hard to manage this session here in this form, which is why I don't like doing it. But let's scroll down to King. I bet it didn't finish the uploading process. Yeah, look, see that? It has attempt in progress, and that means it doesn't even show up in my grade center. So you got to go in and fix that. Now, I can't, you have to finish the attempt in progress before I can check it. You know what I mean?
Yeah.
I suspect that what's going to happen is because you uploaded from your iPad, it's going to end up as a hyperlink. So Kiana, why don't you just send it over to your computer and upload it from there, okay?
All right, sounds good.
That's easy peasy. Okay, but regardless, I'll take it, but I can't have it as an attempt in progress. I need you to finish that submission.
Yeah, I thought it said that it sent successfully, and I just went back in the app, and then it said that there was an error. So I'm just gonna send it from the computer.
Yeah, that sounds good. Okay. All right, so that takes care of that question. Sabrina,
Thank you, by the way.
You got it. You got it.
I'm all set. I'm all set. I'm
All
sorry.
right, I'm going to stop the recording for the benefit of the other asynchronous people.